Imagine standing at the edge of everything you know. Behind you lies all of existence. Every star, every galaxy, every particle of matter and energy that makes up the universe. Ahead of you? What? Is there an edge? Can you step beyond it? Or does the universe go on forever with no boundary? And if there is an edge, what lies on the other side? These questions have haunted humanity for millennia. They're questions about the ultimate nature of reality, questions about what exists and what doesn't. In the 21st century, we have more tools to explore these questions than ever before. We have telescopes that can see to the edge of the observable universe. We have mathematical frameworks that can describe the laws of physics with extraordinary precision. But the fundamental questions remain. What's outside the universe? This is one of the deepest questions we can ask. And to answer it, or to understand why it might not have an answer, we need to explore the cutting edge of cosmology, theoretical physics, and philosophy. This is a journey to the boundaries of knowledge itself. Before we can ask what's outside the universe, we need to define what we mean by universe. In everyday language, the universe means everything that exists, all matter, all energy, all space and time. But in scientific discourse, the term is more nuanced. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It's roughly 93 billion light years in diameter. But the observable universe is not all that exists. Light from distant regions hasn't reached us yet because the universe is only 13.8 billion years old. And due to the expansion of space, light from the most distant regions might never reach us. So the universe is likely much larger than the observable universe. In fact, the universe could be infinite. If the universe is infinite, then outside the observable universe is more universe, regions we can't see but that are nonetheless part of the same universe. But in cosmology, physicists sometimes use universe to mean the totality of all space and time governed by the same laws of physics. In this sense, our universe is the region of space and time governed by the laws of physics we observe. If there are other regions of space and time governed by different laws of physics, those would be separate universes, a multiverse. So the definition of universe depends on context. Now, what do we mean by outside the universe? In everyday language, outside means beyond a boundary. Outside a house means beyond the walls of the house. Outside a city means beyond the boundaries of the city. But for the universe, the concept of outside is more problematic. The universe, by definition, is everything. If there's something outside the universe, then the universe isn't everything. That something else is also part of existence. So asking what's outside the universe is almost asking a contradiction. It's like asking what's beyond everything. One way to resolve this, we could say that the observable universe is the universe we can observe, and outside it means beyond the cosmic horizon. Regions we can't see, but that might still be part of a larger universe. Another way, we could say that universe means a region of space and time governed by a particular set of laws of physics, and outside means regions governed by different laws, a multiverse. A third way, we could say that the word outside doesn't really apply to the universe at all, because the universe is not embedded in anything larger. The universe is all there is, and there is no outside. These different interpretations lead to very different answers to our question. The question, what's outside the universe, highlights a fundamental puzzle about existence itself. We're accustomed to thinking of objects as existing in a space. A book exists in a room. The room exists in a building. The building exists in a city. But what does the universe exist in? According to modern physics, space and time are not containers that exist independently of the universe. Space and time are part of the universe. So the question, what does the universe exist in, seems to presume a false picture. A picture where space and time are containers that exist independently. If space and time are part of the universe, then the universe doesn't exist in anything. It just exists. This resolves one puzzle. We don't need to postulate some external container that the universe exists in, but it creates another puzzle. If the universe is self-contained, if there's no external space or time, then in what sense can we talk about anything being outside it? The answer might be that we can't. The concept of outside might presume a spatial container, and if there's no such container, then the concept doesn't apply. In that case, asking what's outside the universe would be asking an incoherent question, a question that doesn't have an answer because the question itself is based on a mistaken assumption. But let's explore this more carefully. Perhaps there are coherent ways to interpret the question, even if the naive interpretation is problematic. A key concept in cosmology is the cosmic horizon. The cosmic horizon is the boundary of the region from which light has had time to reach us. Light travels at a finite speed. The universe is only about 13.8 billion years old. So light from distant regions hasn't had time to reach us. The cosmic horizon is roughly 46 billion light years away, not 13.8 billion light years because of the expansion of space. Beyond the cosmic horizon, there might be more universe, galaxies, stars, planets, perhaps civilizations and life, but we can't see them. They're beyond our cosmic horizon. In this sense, there is something outside the observable universe. There's the rest of the universe beyond the cosmic horizon. But it's not something alien or strange. It's presumably made of the same matter, energy, and governed by the same laws of physics as the observable universe. So in a sense, outside the observable universe is more universe. There are actually different types of horizons in cosmology. A particle horizon is the maximum distance from which a particle could have reached us, given the finite speed of light and the age of the universe. This is the edge of the observable universe. An event horizon is different. It's the boundary beyond which we could never receive a signal, no matter how long we wait. For example, near a black hole, there's an event horizon. Once something crosses it, it can never send a signal back out. In an accelerating universe, which ours appears to be, there's also an event horizon. Far distant galaxies are moved away from us so fast that their light will never reach us, no matter how long we wait. The existence of event horizons raises an interesting question. If we can never know what's beyond the event horizon, in what sense does it exist? This is a philosophical question, but it's relevant to our inquiry. If there are regions of the universe we can never observe or interact with, are they part of our universe or are they separate? Modern cosmology suggests that the Big Bang was preceded by a period of cosmic inflation, exponential expansion. During inflation, the universe expanded so rapidly that regions far beyond what we can see today were once in contact with each other. This inflation explains why the universe is so uniform and isotropic. It also explains the origin of galaxies and large-scale structures through quantum fluctuations during inflation. But inflation also suggests that beyond our cosmic horizon, there is more universe. In fact, if inflation happened, the universe is probably much, much larger than the observable universe. Some physicists estimate that the entire universe might be at least 10 to the 26th power times larger than the observable universe, possibly infinitely larger. So outside the observable universe is vastly more universe, stretching beyond our ability to see. In this sense, we live in a small corner of a much vaster cosmos. According to Einstein's theory of relativity, space and time are not separate. They're woven together into a four-dimensional structure called space-time. Space-time is a manifold, a continuous smooth structure described by geometry. In space-time, events are points, and distances between events are measured by the space-time interval. The key insight is that space-time is not flat. It's curved by the presence of mass and energy. Massive objects curve space-time around them, and this curvature is what we experience as gravity. Now, a crucial question. Does space-time have a boundary? If space-time has a boundary, then there's something outside, beyond the boundary. But what would be beyond a boundary of space-time? Not space or time, because space-time is all the space and time there is. Perhaps nothing. Perhaps the boundary is the edge of existence itself. One way space-time could have a boundary is if it's topologically closed, like the surface of a sphere. On a sphere, there's no boundary. If you travel far enough in one direction, you come back to where you started. The sphere is a closed surface with no edge. Similarly, space-time could be closed. You could travel far enough in one direction and come back to where you started, in space or even in time. A closed universe would have no edge, no boundary, nothing outside. It would be completely self-contained. An open universe, by contrast, has no boundary either, but it's infinite. Like an infinite plane, you can travel forever and never come back. An open universe also has nothing outside because it's infinite. But there's a third possibility. Space-time could have a boundary, like a disk. If you're on a disk, you can reach the edge. But our current observations suggest the universe is either open or closed, with no boundary. The cosmic microwave background observations suggest the universe is flat, neither closed nor open in the sense of having positive or negative curvature. A flat universe could be infinite with no boundary. The topology of the universe, its large-scale shape and structure, is an open question. We know the universe is very nearly flat, based on observations of the cosmic microwave background. But flatness in curvature doesn't determine topology. A flat universe could have different topologies. It could be infinite, stretching forever in all directions, or it could be finite but have a non-trivial topology, like a flat torus, where opposite edges are identified with each other. If the universe has the topology of a flat torus, then the universe is finite, but it has no boundary. There's no edge you could reach. If you traveled far enough in one direction, you'd come back to where you started. Such a universe would answer the question, what's outside, with nothing, because there is no outside. The universe is finite but unbounded like the surface of a sphere, but in 3 spatial dimensions instead of 2. Astronomers have searched for evidence of non-trivial topology by looking for repeated patterns in the cosmic microwave background. If the universe has a small enough non-trivial topology, we might see images of the same regions of space in different directions. So far, no clear evidence for non-trivial topology has been found, but it remains an open possibility. The universe's topology is determined by its geometry and the distribution of matter and energy. We're still working to understand what the universe's true topology is. We mentioned cosmic inflation earlier, Let me explore it in more depth because inflation leads naturally to the idea of a multiverse. Cosmic inflation is a period of exponential expansion that occurred in the first fraction of a second after the Big Bang. During inflation, the universe doubled in size roughly every 10 to the power of minus 36 seconds. This exponential expansion happened for about 10 to the power of minus 32 seconds. By the end of inflation, the universe had expanded by a factor of at least 10 to the 26th power, possibly much more. Inflation was proposed in the 1980s by Alan Guth and others to solve several problems with the original Big Bang theory. One problem was the flatness problem. Why is the universe so flat? Why isn't it more curved? Inflation naturally flattens the universe the way blowing up a balloon flattens the surface. Another problem was the horizon problem. Why is the universe so uniform on large scales? Regions far apart couldn't have communicated, so how did they reach the same temperature? Inflation solves this because regions that seem far apart today were in close contact before inflation blew them apart. Now here's where it gets interesting. In the 1980s, Andre Linde proposed a modification to inflation theory called eternal inflation. In eternal inflation, inflation doesn't simply end everywhere at once. Instead, it ends in some regions, creating bubble universes while continuing in other regions. Think of it like boiling water. When water boils, bubbles form in the water. Each bubble is a region where the water has boiled away. In eternal inflation, bubbles form, regions where inflation ends, while the surrounding space continues to inflate. Each bubble becomes a universe. Our universe is one such bubble. But inflation continues eternally in the space between bubbles, creating more bubbles, more universes. This process never ends. It goes on forever, creating an infinite number of universes. This is the inflationary multiverse, a direct prediction of inflation theory. Eternal inflation has profound implications. First, it predicts that our Big Bang was not the beginning of everything. Our Big Bang was the beginning of our bubble universe, but inflation began earlier, in the parent universe that created our bubble. And before that, there was inflation in the grandparent universe, and so on, back infinitely far. Second, eternal inflation predicts that there are infinitely many bubble universes, each with potentially different physical properties. If the inflaton field, the field responsible for inflation, has different values in different regions, then different bubble universes could have different laws of physics. This connects to the string landscape we'll discuss later. Third, eternal inflation is self-reproducing. Once it starts, it continues forever, creating new universes without end. This means that the multiverse is not a finite collection of universes. It's infinite and constantly growing. Fourth, eternal inflation explains fine-tuning. Why does our universe have the particular laws of physics that allow life? In an inflationary multiverse, there are universes with all possible laws of physics. We observe the universe we do because we live in one of the rare universes where life is possible. This is an anthropic explanation. It's controversial, but it follows logically from eternal inflation. Eternal inflation is elegant and appealing, but it faces challenges. One challenge is that eternal inflation makes testable predictions very difficult. If there are infinitely many universes with all possible properties, how do we test the theory? Different physicists have proposed different solutions. Some invoke measure problems, ways of assigning probabilities to different universes in the multiverse. Others argue that eternal inflation can make predictions about our observable universe's properties. and these predictions can be tested. But measuring the predictions is difficult because we only have access to one universe. Another challenge is that eternal inflation requires the inflaton field to have a particular form. It needs to be able to sustain inflation in some regions while ending in others. Not all inflation models naturally produce eternal inflation. Some end everywhere at once. So eternal inflation is not a universal prediction of all inflation theories, only some. A third challenge is conceptual. If eternal inflation creates infinitely many universes, can we even call it a scientific theory? Science usually aims to make falsifiable predictions. But if infinitely many things happen, how do we test the theory? Some physicists argue that eternal inflation is science because it follows from well-motivated physics and makes definite, if difficult to test, predictions about probabilities. Others argue that eternal inflation has crossed the line into metaphysics, speculation about things that are fundamentally unobservable. Despite these challenges, eternal inflation is taken seriously by many cosmologists. It's a natural prediction of inflation, and it offers a framework for understanding the apparent fine-tuning of our universe's properties. Another major source of multiverse ideas is string theory. String theory proposes that fundamental particles are not point-like objects, but tiny vibrating strings. Different modes of vibration of the string correspond to different particles. For example, one vibrational mode might be an electron, another an electron neutrino, another a photon. String theory is a quantum theory of gravity. It attempts to unify quantum mechanics with general relativity. The theory is mathematically beautiful and elegant, but it has a peculiar feature. It has an enormous number of solutions. Each solution corresponds to a possible universe with different laws of physics. This collection of solutions is called the string landscape. The landscape is vast. Estimates suggest there are roughly 10 to the power of 500 different solutions to string theory equations. Each of these 10 to the power of 500 solutions corresponds to a possible universe. If all of these solutions are realized, if all of these possible universes actually exist, then we have a multiverse of 10 to the power of 500 universes. An obvious question: if there are 10 to the power of 500 possible universes in the string landscape, which one do we live in? Our universe has specific properties, specific values for the fundamental constants, specific geometry for spacetime, a specific set of particles and forces. Why our universe and not another? String theorists face a problem. They can't predict which solution we live in from first principles. The theory predicts many possible universes, but not which one is realized. This is troubling because it seems to rob the theory of predictive power. If the theory can accommodate any set of observed properties by choosing the right solution in the landscape, then how can it be tested? One response is to invoke the anthropic principle. The anthropic principle says that we should not be surprised to find ourselves in a universe with properties compatible with our existence. After all, we only exist because our universe happens to have the right properties. So even though most universes in the string landscape are incompatible with life, we should expect to find ourselves in one of the rare universes that does permit life. This anthropic explanation is controversial. Some physicists embrace it. Others argue that it's not truly scientific. It's an admission that the theory can't make predictions. But if string theory is correct, and if the string landscape is real, then the anthropic principle might be the right way to think about our place in a multiverse of 10 to the power of 500 universes. Here's an interesting connection. Eternal inflation and the string landscape can work together. In eternal inflation, different bubble universes can have different physical properties. In string theory, different points in the string landscape correspond to different sets of physical properties. So eternal inflation could populate the string landscape. Different bubble universes could correspond to different solutions of string theory. In this picture, eternal inflation creates an infinite number of bubble universes, and eternal inflation gradually explores all, or most, of the 10 to the power of 500 solutions in the string landscape. The result is an infinite multiverse where all possible universes are realized somewhere. This unifies two major sources of multiverse ideas, inflation and string theory, but it also raises the stakes for the multiverse hypothesis. If it's true, then our universe is one of infinitely many, governed by one of 10 to the power of 500 possible sets of physical laws. In a cosmos that never stops creating new universes, we would be just one universe among an incomprehensibly vast multiverse. The string landscape is controversial, even among physicists who work on string theory. Some criticisms are technical. There's debate about whether the 10 to the power of 500 estimate is correct, whether all solutions are stable, and whether the solutions correspond to truly distinct universes or are just different mathematical descriptions of the same physics. Other criticisms are more fundamental. One criticism is that the string landscape makes string theory unfalsifiable. If any conceivable universe could be a solution of string theory, then the theory can't be tested. Critics argue that a scientific theory must make precise predictions that can be contradicted by observation. String theory, with its vast landscape, doesn't do this. Proponents respond that string theory does make predictions about the properties of our particular universe, and these predictions can be tested even if we can't test the existence of other universes in the landscape. Another criticism is that the string landscape relies on the validity of eternal inflation, but eternal inflation itself is speculative and difficult to test. If eternal inflation doesn't occur, then the string landscape might not be realized. The different solutions might remain abstract possibilities rather than actual universes. A third criticism is more philosophical. Some argue that invoking 10 to the power of 500 universes to explain the properties of our universe is not elegant or parsimonious. It seems to multiply entities beyond necessity. These criticisms are serious, and they reflect genuine disagreements within the physics community. But despite the controversies, many physicists take the string landscape and the multiverse idea seriously. It's an active and vibrant area of research. Here's a multiverse idea that comes from quantum mechanics itself. In quantum mechanics, a system can exist in a superposition of multiple states. According to the Copenhagen interpretation, when we measure the system, the superposition collapses to one definite state. But in 1957, physicist Hugh Everett proposed an alternative interpretation, the many worlds interpretation. In the many worlds interpretation, when we measure a quantum system, the superposition doesn't collapse. Instead, the universe branches into multiple branches, one for each possible outcome. For example, suppose a quantum particle is in a superposition of being at location A and location B. In the Copenhagen interpretation, when we measure it, the superposition collapses, and we find it at A or B with some probability. In the many worlds interpretation, when we measure it, the universe branches. In one branch, the particle is at A. In another branch, it's at B. Both branches are equally real. We experience one branch, let's say the one where it's at A, but the other branch exists too, experienced by another version of us who sees it at B. The many worlds interpretation has a startling implication. Every quantum event that could happen does happen in some branch of the multiverse. Every time a quantum measurement occurs with multiple possible outcomes, the universe branches, with each outcome realized in a different branch. This happens constantly. Quantum events occur throughout the universe at every moment. Each one causes branching. The result is a vast, infinitely branching tree of universes. We live in one branch, but countless other branches exist, each with a slightly different history. Some branches have the same large-scale properties as our universe, but differ in small details. Others differ in major ways. In some branches, key historical events happen differently. In some branches, you made different choices in your life. All of these branches are equally real, according to the many worlds interpretation. This is a multiverse arising not from cosmology or string theory, but from quantum mechanics itself. The many worlds interpretation raises profound philosophical questions. If all possible outcomes of quantum measurements are realized in some branch, then in a sense, everything that can happen does happen. This seems to deny the reality of choice and probability. If both outcomes happen, then in what sense did we choose one outcome? Proponents of many worlds respond that probability still applies. It describes which branch you're in, given the quantum state. But all branches are realized. Another implication: if many worlds is true, then the universe is incomprehensibly vast. Not just 10 to the power of 500 universes, as in the string landscape. Not just infinitely many bubble universes in eternal inflation. In many worlds, the number of branches grows exponentially with time. The branching tree has roughly 2 to the power of n branches, where n is the number of quantum events that have occurred. Given that quantum events occur everywhere, constantly n is astronomically large. The number of branches is unimaginably vast. This raises a question about probability and measure. If there are infinitely many branches, how do we assign probabilities? This is called the measure problem. It's a serious technical issue in the many worlds interpretation. One criticism of many worlds is that it's unfalsifiable. If all outcomes happen, how can we test the theory? Proponents respond that many worlds is not unfalsifiable. It makes predictions about the probabilities of different outcomes in experiments. These predictions are the same as in the Copenhagen interpretation, so any experiment that tests quantum mechanics tests both interpretations. But there might be subtle differences. Some physicists have proposed experiments that could, in principle, distinguish many worlds from other interpretations. For example, if many worlds is true, then quantum computers might be able to perform certain computations more efficiently by exploiting the branching structure of the multiverse. But these are speculative ideas. Currently, there's no experimental evidence that decisively favors many worlds over other interpretations. Many worlds remains a philosophical interpretation of quantum mechanics, not a well-established scientific fact. But it's taken seriously by many physicists, and it's philosophically rich. It suggests that the universe is far larger and stranger than our everyday experience suggests. We perceive 3 spatial dimensions: left, right, forward, backward, up, down. We also perceive time as a 4th dimension, but there's no fundamental reason why space should have only 3 dimensions. In fact, many theories in modern physics suggest that there are extra spatial dimensions beyond the 3 we perceive. String theory requires extra dimensions. In most formulations, string theory requires 10 space-time dimensions, 9 spatial plus 1 temporal. So where are these extra 6 spatial dimensions? If they exist, why can't we see them? One possibility: they're compactified. This means they're curled up into a small, compact space that we can't directly observe. Imagine a garden hose. From far away, it looks one-dimensional, a line, but close up you see it has a circular cross-section. It actually has two dimensions, length and circumference, but the circumference is so small that we don't notice it from a distance. Similarly, extra spatial dimensions could be curled up at tiny scales, around 10 to the power of minus 35 meters or smaller, so small that we can't perceive them directly. But even though we can't perceive them, they would affect physics at high energies. In string theory, the extra dimensions are compactified into complex geometric shapes called Calabi-Yau manifolds. A Calabi-Yau manifold is a six-dimensional geometric structure with special properties. There are countless possible Calabi-Yau manifolds. Estimates suggest roughly 10 to the power of 500 distinct ones. Different Calabi-Yau geometries correspond to different solutions in the string landscape. The topology and geometry of the compactified dimensions determine the fundamental constants and particle spectrum of the universe. So the shape of the extra dimensions determines what physics we see. This is remarkable. It suggests that the properties of our universe, the strength of gravity, the masses of particles, the coupling constants, are all determined by the geometry of tiny hidden extra dimensions. Calabi-Yau manifolds are beautiful mathematical objects. They have intricate structure of folds, holes, and tunnels at all scales. Visualizing them is difficult because they exist in 6 dimensions, beyond what our three-dimensional brains can easily comprehend. But mathematicians have developed sophisticated tools to study them, and physicists use them to build models of particle physics. Most discussions of extra dimensions assume they're compactified at very small scales. But some theoretical physicists have explored the possibility of large extra dimensions. In models with large extra dimensions, the extra dimensions could be much larger than 10 to the power of minus 35 meters. They could be millimeters or centimeters across. Such dimensions would still be invisible to us, not because they're too small, but because ordinary matter and light are confined to a three-dimensional surface called a brane. A brane is a subspace within a higher dimensional space. Think of it like a sheet of paper embedded in three-dimensional space. If ordinary matter is confined to a three-dimensional brane, we would only perceive 3 spatial dimensions, even if there are more. Gravity, however, might not be confined to the brane. It might propagate through the extra dimensions. This would explain why gravity is so weak compared to other forces. Gravitational force spreads out into the extra dimensions, diluting its strength. Large extra dimensions were proposed by physicists Nima Arkani-Hamed, Savas Dimopoulos, and Giad Vali in the late 1990s. They suggested that extra dimensions could be large enough to affect physics at the scale of millimeters or smaller. This could be tested at future colliders by looking for signatures of gravity in the extra dimensions. The concept of brane worlds extends the idea further. In a brane world, our entire three-dimensional universe, the observable universe, is a three-dimensional brane embedded in a higher dimensional space. The higher dimensional space is called the bulk. Ordinary matter and forces are confined to the brane. We can't escape the brane or perceive the bulk directly, but the bulk might contain other branes, other three-dimensional universes. Different branes might have different physical properties. They might host different particles and forces. From the perspective of observers on one brane, other branes are invisible and inaccessible, but they're part of the same higher dimensional space. This is a form of multiverse. The multitude of universes are all embedded in a higher dimensional bulk. An influential brain world model is the Randall-Sundrum model, proposed by Lisa Randall and Raman Sundrum in 1999. In this model, there are two brains in a five-dimensional bulk. Our universe is one view brain. Another brain with different physics is the other. Gravity is stronger on the other brain, which might explain some puzzles in particle physics. The Randall-Sundrum model is speculative, but it shows how extra dimensions could lead to a multiverse of parallel universes. Let me delve deeper into the mathematics of higher dimensions. Most people find it hard to visualize 4 dimensions, let alone 6, 10, or 11. But mathematicians can reason about higher dimensional spaces abstractly using geometry and topology. A point is 0-dimensional. A line is 1-dimensional. A plane is 2-dimensional. Our space is 3-dimensional. Space-time is 4-dimensional. 3 space plus 1 time. We can generalize this to any number of dimensions. A 4-dimensional hypersphere, also called a 3-sphere or globe, is the set of all points equidistant from a center in 4-dimensional space. Just as a circle is the 1-dimensional boundary of a 2-dimensional disk, and a sphere is the 2-dimensional boundary of a 3-dimensional ball, a 3-sphere is the 3-dimensional boundary of a 4-dimensional ball. A 3-sphere is finite in volume but has no boundary. If you lived on a 3-sphere, you could travel infinitely far without reaching an edge, but the total volume would be finite. Similarly, we can construct higher dimensional analogs, 4 spheres, 5 spheres, and so on. Each of these is a boundless finite space. Beyond hyperspheres, there are more exotic higher dimensional shapes. A torus is the shape of a donut. In higher dimensions, you can construct higher dimensional tori. A 4-dimensional torus, for example, is the product of 2 circles. It's finite and boundless, but with a different topology than a 3-sphere. There are also manifolds with more complex topology, projective spaces, lens spaces, and many others. Each of these higher dimensional shapes could, in principle, be the large-scale shape of the universe. If our universe's large-scale geometry is a 4-dimensional torus, for example, then the universe would be finite but with no boundary. Travel far enough in one direction and you'd come back where you started, just as on Earth, if you travel far enough in one direction, you circle the globe. Or if the universe's geometry is a hyperbolic space, infinite and negatively curved, then you could travel forever without returning. Different topologies have different implications for cosmology. They affect the distribution of galaxies, the path of light rays, and the possible structures that could form. Astronomers have searched for evidence of non-trivial topology by looking for patterns in the cosmic microwave background. So far, observations are consistent with the simplest topologies, but more exotic ones haven't been ruled out. How do higher dimensional structures relate to the multiverse? One way, in string theory and brain world models, the extra dimensions might host other universes. A 4-dimensional universe is a brain in a higher dimensional bulk, but the bulk itself might be very large, with many brains in it. Each brain is a universe. Different brains have different dimensions, different properties. In principle, the bulk could be extremely complex, with countless brains at various locations and orientations. From the perspective of observers on one brain, other brains are inaccessible, but they're part of the same higher dimensional structure. Another way, the topology of our own universe might be more complex than we think. If the universe has non-trivial topology, then distant regions that seem far apart might actually be connected. For example, if the universe has the topology of a torus, then opposite edges of the observable universe are identified. They're the same place, just on different sides of the identified boundary. This could create strange geometric effects. You might be able to see light from a distant galaxy arriving from multiple directions if the light has traveled through the identified regions. These geometric exotica suggest that space itself could have a structure far more intricate than the simple Euclidean or spherical geometry we're accustomed to. How much of this is science and how much is speculation? Extra dimensions and brane worlds are genuine theoretical frameworks developed by serious physicists using rigorous mathematics. They arise naturally from string theory, one of the leading candidates for a theory of quantum gravity. But they're speculative because we have no direct observational evidence for extra dimensions or brane worlds yet. We can search for signatures of extra dimensions in particle accelerator experiments. If extra dimensions exist and are large enough, they might produce detectable effects at high energies. The Large Hadron Collider has searched for such signatures. So far, none have been found. But the search continues. Similarly, we can search for signatures of non-trivial topology in the cosmic microwave background. These searches are genuine science. They test specific predictions that follow from the theories. But the existence of extra dimensions remains an open question. It's not established fact. Here's a provocative idea. What if physical reality is identical to mathematical reality? In other words, what if the universe is not made of some fundamental substance, but is instead a mathematical structure? This is the mathematical universe hypothesis, proposed by physicist Max Tegmark. According to this hypothesis, any mathematically consistent structure exists, not just in abstract mathematical space, but as a concrete physical reality. This seems strange. How can abstract mathematics be physical reality? But consider, everything we know about physics is ultimately mathematical. The laws of physics are described by equations. Particles are described by quantum fields. Space-time is described by geometry. We've never observed any aspect of physical reality that isn't ultimately mathematical, so perhaps mathematics is not merely a language we use to describe reality. Perhaps mathematics is reality. If this is true, then all possible mathematical structures, all possible logically consistent universes, actually exist. Not just the universe we observe, but all possible universes. Tegmark proposed a hierarchy of multiverses based on different levels of mathematical structure. Level 1, the observable multiverse. This is the multiverse of eternal inflation. Regions of space beyond our cosmic horizon governed by the same laws of physics as us. This is not speculative. It follows from established inflation theory. Level 2, the inflationary multiverse with different physical laws. Different bubble universes have different values of fundamental constants and different particle content. This also follows from inflation, if slightly more speculatively. Level 3, the quantum multiverse. This is the many worlds interpretation of quantum mechanics. Different branches of the wave function correspond to different universes. Level 4, the mathematical multiverse. All logically consistent mathematical structures exist as physical realities. This is the most speculative level, but it follows from the principle that if mathematics equals reality, then all mathematics exists physically. Each level is more speculative than the previous, but they're all justified by the same basic reasoning. If a structure is mathematically consistent, it exists. The mathematical universe hypothesis has profound implications. If true, it explains the apparent fine-tuning of our universe. Our universe appears designed for life because it's one among all possible universes, and we naturally find ourselves in one where life is possible. It also provides an ultimate answer to the question, what's outside the universe? Answer, all other possible universes. Our universe exists in the space of all logically consistent mathematical structures, but the hypothesis faces serious criticisms. One criticism is that it's unfalsifiable. If all mathematically consistent structures exist, then any observation is consistent with the theory. How can it be tested? Another criticism is that the hypothesis seems to multiply entities beyond necessity. Invoking infinitely many universes to explain one seems extravagant. A third criticism is that the hypothesis conflates existence with logical consistency. Just because something is mathematically consistent doesn't mean it exists. Unicorns are logically consistent, but they don't exist in the real world. Proponents respond that in the context of fundamental physics, we have no way to distinguish existence from logical consistency. The laws of physics are consistent mathematical structures. There's no deeper fact of the matter about which structures exist. The mathematical universe hypothesis remains controversial, but it's taken seriously by some leading physicists. It represents an extreme extrapolation from the success of mathematics in describing nature. This is perhaps the deepest question in philosophy. Why is there something rather than nothing? Why does the universe exist at all? This question is deeply puzzling. It seems that the default state, the most natural state, would be nothing. No universe, no matter, no energy, no space, no time. Yet we observe a universe. Why? Some philosophers argue that this question has no answer. Existence is a brute fact, unexplainable by reference to anything deeper. Others argue that we can explain existence by reference to logical necessity. Perhaps it's a necessary truth that something exists. But this seems wrong. Necessity applies to logical truth, like 2 plus 2 equals 4. But the existence of the universe seems contingent. It could have been otherwise. Historically, many people have invoked God as the explanation for existence. God is the necessary being, the ultimate cause that explains why anything else exists. This is a metaphysical explanation. It appeals to something beyond the physical. But the God hypothesis raises its own questions. If God exists necessarily, why must God exist? Is God's existence explained by some deeper principle? Some philosophers of religion argue that God is the necessary foundation of existence, the ground of being. God's existence is self-explanatory. God is the explanation of God's own existence. But this seems circular. It's unclear what it means to be self-explanatory or self-causing. Some physicists and philosophers have tried to give physical explanations of existence. One approach, appeal to quantum mechanics. In quantum mechanics, events can occur without a cause, with some probability. Virtual particles constantly pop in and out of existence in the quantum vacuum. Some physicists, including Stephen Hawking, have suggested that the universe itself could be a quantum fluctuation, a virtual universe that fluctuated into existence from the quantum vacuum. If the universe has no net energy, positive energy balanced by gravitational potential energy, then such a fluctuation wouldn't violate conservation of energy. The universe would exist because quantum mechanics allows it to exist. This is an appealing explanation, but it raises questions. Why should quantum mechanics exist? Why should there be a quantum vacuum? Another approach, appeal to the anthropic principle. We observe a universe because we exist in one. It's no surprise that we find ourselves in a universe that permits life. That's a necessary condition for us to observe anything. This doesn't explain why universes exist, but it explains why we observe the particular universe we do. Perhaps the question, why is there something rather than nothing, has no answer. Every explanation appeals to something more fundamental. Why does that more fundamental thing exist? That requires an even more fundamental explanation. This regress can't go on forever. Eventually, we reach something that's not explained by reference to anything deeper. Call this the ultimate explanation. It's either brute fact, logical necessity, or self-explanatory. If it's a brute fact, just the way things are, then existence ultimately has no explanation. If it's logically necessary, then some mathematical or logical structure must necessarily exist. But why that structure? If it's self-explanatory, we need to understand what self-explanation means. Perhaps the answer is that we'll never fully understand why the universe exists. It might be a question beyond the reach of human knowledge. Another deep issue, causation. In everyday life, we understand causation simply. A cause is an event that brings about an effect. If I push a ball, the push is the cause. The ball rolling is the effect. But in physics, the notion of causation is more subtle. In classical mechanics, we have deterministic laws. Given the initial conditions and the laws, the future state is completely determined. Does this mean the past causes the future? Not exactly. The initial conditions and laws together determine the future, but we don't usually call the initial conditions a cause. In quantum mechanics, the situation is even stranger. Quantum events are probabilistic. They don't have causes in the classical sense. A radioactive nucleus decays. There's no deeper fact about why it decayed at that particular moment. It's a fundamentally random event. So at the quantum level, causation breaks down. There are events without causes. Here's a puzzle. The fundamental laws of physics are time symmetric. If you film a physics experiment and play it backward, the backward film looks like a valid physics experiment, with some exceptions involving weak interactions. In other words, the laws themselves don't distinguish between forwards and backwards in time. Yet we experience a clear direction of time. The past is fixed. The future is open. We remember the past, but not the future. Why is there an arrow of time? The answer is thermodynamics. The second law of thermodynamics says that entropy, disorder, increases over time. The universe began in a low entropy state, the Big Bang. It's been increasing in entropy ever since. This increase in entropy defines the arrow of time. The forward direction in time is the direction of increasing entropy. But why did the universe begin in a low entropy state? That's a deep question in cosmology. If the universe could start in any state with equal probability, it's overwhelmingly more likely to start in a high entropy state. Yet we observe a low entropy beginning. Why? One possibility, initial conditions. The Big Bang simply began in a low entropy state as a matter of fact. This is a brute fact, unexplainable by reference to anything deeper. The notion of causation becomes problematic in cosmology. If the universe has a beginning, what caused the universe? We instinctively want to say something caused the Big Bang. But at the quantum level, events can occur without causes. Perhaps the Big Bang was a quantum event, a fluctuation that occurred without a cause. But this seems unsatisfying. It still leaves the question, why did that particular quantum fluctuation occur? Why did the universe come into being? Some physicists argue that the question, what caused the Big Bang, is malformed. Causation presumes time. A cause is an event that occurs before an effect. But time itself began at the Big Bang. There is no before the Big Bang. So asking what caused the Big Bang is like asking what's north of the North Pole. The question presumes a framework, time in the first case, space in the second, that doesn't apply. In this view, the Big Bang is the beginning of time, not an event in time. It has no cause because causation doesn't apply to it. Interestingly, general relativity permits solutions with closed time-like curves, paths through space-time that form closed loops in time. A closed time-like curve would allow an object to travel forward in time, eventually looping back to its starting point in both space and time. In other words, it would be possible to travel into the future and back to the past. General relativity permits such solutions. The Kerr metric, which describes rotating black holes, and some other solutions contain closed time-like curves. But whether such curves actually exist in our universe is unknown. If closed time-like curves exist, then backwards causation would be possible. You could travel back in time and interact with the past. This raises paradoxes. The grandfather paradox: you could travel back and kill your grandfather, preventing your own birth, but you did exist. Contradiction: various solutions have been proposed. One is the many worlds interpretation. If you travel back and change history, you create an alternate timeline. Your original timeline still exists. Another is the Novikov self-consistency principle. The laws of physics conspire to prevent paradoxes. If you try to create a paradox, you will fail. Your gun jams, your aim is off. Physics prevents the paradox. Closed time-like curves remain speculative, but they show how strange the implications of general relativity can be. They also show that the arrow of time might not be as fundamental as it seems. At least in principle, time travel might be possible. In quantum mechanics, observation plays a special role. Before a measurement, a quantum system exists in a superposition, multiple states at once. When we measure the system, the superposition collapses to one definite state. This seems to suggest that observation is fundamental. Without observation, there's only superposition. With observation, reality becomes definite. This is deeply strange. It seems to imply that consciousness plays a fundamental role in physics. Some early quantum pioneers, like John von Neumann and Eugene Wigner, speculated that consciousness might be necessary to collapse the wave function. But most modern physicists reject this interpretation. Instead, they argue that observation just means interaction. When we measure a system, we interact with it, and this interaction causes the superposition to collapse. Consciousness is not special. Any sufficiently sensitive interaction can cause collapse. But the measurement problem persists. How does collapse occur? The Schrödinger equation describes how the wave function evolves before measurement. But what causes the collapse? Different interpretations of quantum mechanics handle this differently. The Copenhagen interpretation says collapse is a fundamental postulate. It happens, but we don't explain why. The many worlds interpretation says there's no collapse. The universe branches into multiple outcomes, all equally real. The pilot wave theory says the wave function never collapses. Instead, particles have definite positions guided by the wave function. The objective collapse theories propose that collapse is a physical process that occurs spontaneously, described by modified equations. These interpretations make the same predictions about the results of experiments, so we can't test them directly. But they have very different metaphysical implications. Many worlds implies an enormous multiverse. The Copenhagen interpretation implies a fundamental role for measurement. Pilot wave theory implies a non-local guiding influence. The interpretation you adopt depends on your philosophical views about the nature of reality. There's a deep philosophical puzzle at the heart of quantum mechanics. The quantum formalism seems to presume an observer external to the system being observed. The observer measures the system, causing collapse. But in reality, the observer is part of the universe. Observers are made of atoms which obey quantum mechanics. So when you measure a system, you, the observer, become entangled with the system. Your brain is now in a superposition of states corresponding to the different possible measurement outcomes. But you don't experience a superposition. You experience one definite outcome. This is the measurement problem. It's not just about systems in the lab, it's about the entire universe. The universe contains many observers. Each observer measures various systems. According to quantum mechanics, the universe should be in a vast superposition of all possible combinations of measurement outcomes. But we don't observe this, we observe definite classical outcomes. Why does the quantum superposition collapse to a classical world? This is one of the deepest unsolved problems in quantum mechanics. Some physicists think the solution is decoherence. Interactions with the environment cause superpositions to effectively collapse. Others think many worlds is correct. The superposition doesn't collapse. The universe branches. Still others think we need new physics beyond quantum mechanics to explain the emergence of classicality. These puzzles about observation and measurement have profound implications. They suggest that reality might be fundamentally different from our classical intuitions. Perhaps reality is not made of definite objects with definite properties existing independently of observation. Perhaps reality is fundamentally probabilistic, with definite properties only coming into existence when observed. Or perhaps reality is a vast superposition of all possible states, with consciousness or decoherence selecting which state we perceive. Or perhaps many worlds is correct, and all possible outcomes are real, existing in parallel branches. These are radical departures from our everyday understanding of reality. But they follow from taking quantum mechanics seriously, at its most basic level. What quantum mechanics is telling us is that the universe is not a collection of objects with definite properties. It's something deeper and stranger. The implications are still unclear, but they suggest that the ultimate nature of reality might be radically different from what we assume. We've explored many different ideas about what lies outside the universe, but we found that the answer depends on what we mean by universe. If universe means the observable universe, the region from which light has reached us, then outside it is more universe, beyond our cosmic horizon. These regions are presumably made of the same matter and governed by the same laws of physics. If universe means the region of space and time governed by a particular set of laws of physics, then outside it are other regions governed by different laws, other universes in a multiverse. According to eternal inflation, there are infinitely many such universes. According to string theory, there are around 10 to the power of 500 such universes in the string landscape. If universe means all of space-time with no boundary, then there is nothing outside because there's nothing beyond space-time. Space-time is all there is. The question, what's outside, presumes a boundary, but space-time has no boundary. If universe means all logically consistent mathematical structures, then outside our universe are all other mathematical structures, the entire landscape of mathematical possibility. According to the mathematical universe hypothesis, all such structures exist. The different perspectives we've explored, cosmological, quantum mechanical, and philosophical, are actually interconnected. Eternal inflation from Cosmology predicts a multiverse of bubble universes. The string landscape from string theory provides the structure that eternal inflation explores. Many worlds from quantum mechanics suggest another form of multiverse, branching universes. The mathematical universe hypothesis from philosophy suggests that all logically consistent structures exist. The ultimate multiverse. These aren't inconsistent. In fact, they might be different aspects of the same underlying reality. Perhaps eternal inflation populates the string landscape, creating bubble universes with different physical laws. Within each bubble universe, quantum mechanics applies, creating branching worlds. And all of this fits within the larger framework of the mathematical universe hypothesis. All logically consistent structures exist. In this synthesis, our universe is one bubble in an infinitely large inflationary multiverse, one point in the vast landscape of string theory solutions, one branch of a quantum many-worlds tree, and one mathematical structure among all possible structures. We are nested within multiple layers of multiverse. One of the most important connections is through anthropic reasoning. Our universe appears fine-tuned for life. The fundamental constants, the strength of gravity, the mass of the electron, the strength of the strong nuclear force, have values that permit the formation of stars, planets, and life. If any of these constants were slightly different, the universe would be sterile. This fine-tuning is puzzling. Why do the constants have these particular values? One answer: God chose these values. But this is a metaphysical answer, not a scientific one. Another answer: the constants must have these values for some deep mathematical reason, but no such reason has been found. A third answer: anthropic selection. There are many universes with different constants. In most, life doesn't form, but in some, including ours, it does. We naturally find ourselves in one of the life-permitting universes. This anthropic explanation works only if there are many universes. The multiverse hypotheses we've discussed provide the required many universes. If eternal inflation is correct, there are infinitely many bubble universes with different properties. We observe ours because we live here. If the string landscape is correct, there are 10 to the power of 500 possible universes. We observe ours because it's one of the rare ones that permits life. This anthropic reasoning is controversial. Some physicists embrace it. Others argue it's not truly scientific. It's an admission that we can't predict what we observe. But if the multiverse is real, anthropic reasoning might be unavoidable. We can't predict which universe we'd live in, but we can predict that we'd live in one compatible with our existence. Let me try to paint a comprehensive picture of the landscape of possibilities. At the largest scale, according to the mathematical universe hypothesis, there's a space of all logically consistent mathematical structures. This is the ultimate multiverse, all possible universes. Within this landscape, certain structures are simpler or more natural than others. One such structure is the string theory landscape, roughly 10 to the power of 500 possible configurations, each specifying a set of physical laws. If string theory is correct and the string landscape is realized, then 10 to the power of 500 universes exist, one for each configuration. But it's unlikely that all 10 to the power of 500 configurations are realized. Instead, eternal inflation probably populates a large subset of the landscape. Eternal inflation begins in some initial region of space-time. It expands exponentially, creating bubble universes. Different bubbles settle into different configurations in the string landscape. The result is a vast, infinitely growing tree of bubble universes. Within each bubble universe, quantum mechanics applies. The wave function of the universe evolves according to the Schrödinger equation, creating a superposition of all possible histories. According to many worlds, all possible quantum outcomes are realized in different branches. So each classical universe, each bubble in eternal inflation, branches into many quantum worlds. The result is a staggeringly complex structure. Infinitely many bubble universes, each with 10 to the power of 500 possible physical configurations, each branching into infinitely many quantum worlds. This is a multiverse of unimaginable scope. Yet according to the mathematical universe hypothesis, this is just a tiny corner of the space of all possible structures. There are other possible universes not captured by string theory or inflation. There are universes with completely different laws of physics, different dimensions, different logical structures. All of these exist, according to the hypothesis. It's important to note the degrees of speculation here. Some ideas are well supported by observation and theory. Others are more speculative. The observable universe is well established. We have strong observational evidence for its properties. Cosmic inflation is well supported. The cosmic microwave background matches inflation's predictions remarkably well. Eternal inflation is more speculative. It's a natural prediction of inflation, but it's difficult to test. The string landscape is even more speculative. String theory itself is unproven, and the landscape is a prediction of string theory. The many worlds interpretation is speculative. It's one interpretation of quantum mechanics, but not the only one. It makes the same predictions as other interpretations. The mathematical universe hypothesis is highly speculative. It's an interesting philosophical idea, but it's far from proven. As we go down this list, we move from well-established science to increasingly speculative theoretical physics to pure philosophy. A responsible scientist must be clear about these distinctions. We should not claim that the mathematical universe hypothesis is established science. It's a speculative philosophical idea, motivated by the success of mathematics in physics, but it remains unproven and possibly unprovable. But we also should not dismiss these speculative ideas as worthless. They represent serious attempts by physicists to understand the deepest questions about reality. They guide research. They suggest new experiments. They inspire new theories. Even if they turn out to be wrong, the process of exploring them advances our understanding. Let me be clear about what we actually know, based on observations and well-established theory. We know that the observable universe extends at least 46 billion light-years in all directions. We know it contains roughly 2 trillion galaxies, each with hundreds of billions of stars. We know the universe is expanding and that this expansion is accelerating. We know the universe had a hot, dense beginning about 13.8 billion years ago, the Big Bang. We know the universe is governed by quantum mechanics at small scales and general relativity at large scales. We know the fundamental constants, the strength of gravity, the masses of particles, the coupling constants, have specific values. These are established facts, supported by overwhelming observational evidence. Beyond this, things become less certain. We infer that the universe continues beyond our observable horizon. This is based on the assumption that the universe is roughly homogeneous and isotropic. This assumption is well supported but not definitively proven. We infer that cosmic inflation occurred. This is based on the cosmic microwave background pattern, which matches inflation's predictions. But inflation is not directly observed. We infer that eternal inflation might occur. This follows from inflationary models, but we have no direct observational evidence. We speculate that string theory might be correct and the string landscape might be realized. But we have no evidence for string theory or extra dimensions. We debate the interpretation of quantum mechanics, Copenhagen, many worlds, pilot wave, or something else. The interpretations make the same predictions, so we can't test them directly. A key limitation is that we can only observe our observable universe. By definition, we can't observe regions beyond our cosmic horizon. Light from those regions hasn't reached us yet, and might never reach us if the universe continues expanding. So we can never directly observe whether the universe continues beyond our horizon. We can only infer it based on assumptions about the universe's structure. Similarly, we can't directly observe other universes in an inflationary multiverse. They're causally disconnected from us. No signal from them can reach us. We can only infer their existence from the theory that predicts them. This raises a fundamental question. Can we even call the multiverse science? Science usually requires testable predictions. But the multiverse is not directly testable. Some argue that we can test the multiverse indirectly. Different multiverse theories make different predictions about the properties of our observable universe. For example, eternal inflation predicts certain patterns in the cosmic microwave background. Some string theory models predict specific values for the fine structure constant. If we observe that our universe has these predicted properties, that provides evidence for the multiverse theories that predict them. But this is an indirect test. We're not observing the multiverse itself, only inferring it from properties of our universe. There's an ongoing debate among physicists about whether multiverse theories are science. Proponents argue that they are. The multiverse follows from well-established theories, inflation, string theory, quantum mechanics. It makes definite predictions. These predictions can be tested. The fact that we can't directly observe other universes doesn't disqualify the theory. We can't directly observe the past either, but historical science is legitimate. Opponents argue that multiverse theories are not science. They're unfalsifiable. No matter what we observe, we can always claim that other universes have different properties. If the theories make no predictions we can observe or measure, then they're not testable and thus not scientific. This debate reflects a deeper question. What makes something science? Karl Popper argued that science requires falsifiability. A theory is scientific if there's a possible observation that could prove it false. By this standard, theories about unobservable universes are not science. But other philosophers of science argue that Popper's criterion is too strict. Science also includes inference to the best explanation, reasoning about past events, and other methods beyond falsifiability. By this broader standard, multiverse theories could be scientific if they're the best explanation for what we observe. The debate is unresolved. Different physicists have different views about where to draw the line between science and speculation. One important point: all scientific knowledge is provisional. Our best current understanding of the universe is based on the Big Bang theory, cosmic inflation, general relativity, and quantum mechanics. These theories have been tested extensively and have proven remarkably successful. But they might be wrong. They might be approximations to some deeper theory. In fact, we know they're incomplete. General relativity and quantum mechanics are incompatible. They give contradictory predictions at the scale of quantum gravity, around 10 to the power of minus 35 meters. So both theories must be modified or superseded by a deeper theory that encompasses both. String theory is one candidate for this deeper theory, but it's unproven. Other candidates include loop quantum gravity, asymptotic safety, and other approaches. One of these might be correct, or something completely different might replace them. As our understanding deepens, our picture of the universe might change dramatically. The multiverse ideas we've discussed, eternal inflation, the string landscape, many worlds, the mathematical universe hypothesis might turn out to be correct, or they might be dead ends, replaced by better theories we haven't yet imagined. This is the nature of science. It progresses by successive approximations, constantly refining its understanding in light of new observations and better theories. If the multiverse exists, what does it mean for our place in the cosmos? For much of human history, we thought we were at the center of the universe. The Earth was the center, and everything revolved around us. Then Copernicus showed that the Earth orbits the Sun. Then we discovered that our Sun is an ordinary star among billions, in an ordinary galaxy among billions. Then we discovered that our galaxy is just one among 2 trillion observable galaxies. Each discovery moved us further toward the periphery. The multiverse continues this trend to an extreme. We're not just on the edge of the observable universe. We're one universe among infinitely many, or 10 to the power of 500 many. Our universe might not even be typical. It might be a rare exception, one of the few universes capable of supporting life. This is a kind of cosmic humility. We're not special. We're not privileged. We're just one universe among a vast multiverse. But there's another side to this. We are the part of the universe that knows itself. In our universe, complex structures formed, stars, planets, and on at least one planet, life. Life evolved to develop consciousness. Consciousness became self-aware. We are the universe becoming conscious of its own existence. In that sense, we are special. We are the universe's way of understanding itself. This might not seem like much comfort. We're still a tiny speck in an incomprehensibly vast cosmos. But it's a profound truth. Without consciousness, the universe would be just mindless matter and energy, following laws of physics. With consciousness, the universe develops the capacity for meaning, for understanding, for purpose. The multiverse has existential implications. If many worlds is correct, then every possible outcome occurs in some branch of the quantum wave function. This means that in some sense, you are immortal. Every possible continuation of your life, every possible way your life could unfold, is realized in some branch. You might die in this branch, but you survive in others. This is cold comfort. You still die in this branch. The fact that you survive in some other branch doesn't affect your experience of death, but it suggests a kind of immortality, not of the individual in one branch, but of the individual across all branches. Another implication, if there are infinitely many universes, then any sequence of events, no matter how improbable, is guaranteed to occur in some universe. This includes universes with your exact duplicate. There's a universe somewhere with a person physically and psychologically identical to you, with your memories and personality. In fact, if the multiverse is infinite, there are infinitely many such duplicates. Does this matter? Philosophically, it's puzzling. If your duplicate exists, does that change the significance of your death? In some sense, you continue to exist as a duplicate in another universe. But your consciousness is tied to this body. this brain, in this universe. Your duplicate has a separate consciousness. You have no direct access to its experiences. So the existence of duplicates doesn't seem to reduce the finality of death for you, but it does suggest that individual identity is less significant than we usually think. What makes you special is not that you're a unique individual. There are infinite copies of you. What makes you special, if anything, is the particular stream of consciousness you experience in this universe, in this branch of the quantum tree. Does the multiverse make life meaningless? Some people worry that it does. If the universe is infinite, if there are infinite universes, then what significance do our actions have? Does it matter what I do if the outcome occurs somewhere regardless? This is a version of nihilism, the belief that nothing matters. But I think this reasoning is flawed. The significance of your actions is not diminished by the existence of other universes. Your actions determine the course of events in your universe, in your branch of the quantum tree. They affect the people around you. They shape your experience and the experiences of those you interact with. These effects are real and significant, even if other universes exist where you made different choices. Moreover, the multiverse doesn't remove the need for choice. You still have to decide what to do. The fact that some version of you makes one choice and another version makes another choice doesn't relieve you of the responsibility to choose. So I don't think the multiverse undermines meaning. If anything, it deepens meaning. It emphasizes that your choices matter, that your experiences are real, that your consciousness is precious. Ultimately, the multiverse, if it exists, should inspire two complementary attitudes: wonder and humility. Wonder because the universe is far stranger and more vast than we imagined. The idea that there are infinitely many universes, each with potentially different physical laws, each with its own history and future, is breathtaking. It expands our conception of what reality encompasses. It's a kind of cosmic vertigo. When you contemplate the immensity, you become dizzy from the scale, but also humility because it reminds us how little we know. We don't know if the multiverse exists. We don't know if eternal inflation is correct. We don't know if string theory is true. We have theories and speculations, but not definitive answers. The vast majority of the universe, if the multiverse exists, the vast majority of all universes, is beyond our observation. We might never know what lies beyond our cosmic horizon. We might never understand the deepest nature of reality. This should make us humble. It should remind us that despite our scientific progress, there are limits to what we can know. But it should also inspire continued inquiry. The fact that we don't have all the answers is an invitation to keep asking questions. Despite the speculative nature of multiverse theories, physicists are devising ways to test them. One approach is to search for anomalies in the cosmic microwave background that might indicate other bubble universes. If our universe collided with another in the past, it would leave a circular bruise in the microwave background radiation. Astronomers have searched for such bruises. So far, none have been definitively found, but searches continue as our observations improve. Another approach is to look for evidence of extra dimensions. If extra dimensions exist and are large enough, they might affect physics at the scale that future particle accelerators can probe. The Large Hadron Collider and planned future colliders, like the International Linear Collider, will search for signatures of extra dimensions. A third approach is to study the large-scale structure of the universe, the distribution of galaxies. If the universe has non-trivial topology, this might leave signatures in the galaxy distribution and in the cosmic microwave background. Astronomers map the distribution of galaxies and look for patterns that would indicate unusual topology. A fourth approach is to develop better theoretical frameworks. String theory is being refined. Loop quantum gravity and other approaches to quantum gravity are being developed. As these theories improve, they make sharper predictions that can be tested. The hope is that future observations will discriminate between theories, showing which ones are correct and which are wrong. The big picture is this: we live in a universe that we can observe and measure. We can test theories against observations. This is the domain of experimental science. Beyond our observable horizon, there likely lies more universe. We can infer this from theory, but we can't directly observe it. Beyond that, there might be other universes, other regions of space-time with different physical laws. This is the domain of theoretical speculation. And beyond that, there might be the space of all possible mathematical structures, the ultimate multiverse. This is the domain of philosophy. We should treat each domain with appropriate levels of confidence. Observable science deserves high confidence. It's based on evidence and testing. Theoretical speculation deserves lower confidence. It's based on extrapolation from theory, but it's not directly tested. Philosophical speculation deserves even lower confidence. It's based on reasoning about the fundamental nature of reality, but it's far removed from observation. But we should not dismiss the more speculative ideas. They guide research. They inspire new questions. They help us think deeply about the nature of reality. The question, what lies outside the universe, takes us from science to philosophy. The answer depends on what we mean by universe and how far we're willing to speculate. But in asking the question, we engage in one of humanity's most profound activities, trying to understand the cosmos and our place within it. The observable universe is the region from which light has reached us, about 46 billion light years in all directions. Beyond our cosmic horizon lies more universe, presumably similar to what we observe. According to cosmic inflation theory, there are likely many bubble universes beyond our cosmic horizon, each possibly with different physical laws. According to string theory, there are roughly 10 to the power of 500 possible universes in the string landscape. According to quantum mechanics and the many worlds interpretation, there are infinitely many parallel branches of the universe, each representing a different outcome of quantum measurements. According to the mathematical universe hypothesis, there are all possible mathematically consistent structures. The ultimate multiverse. These ideas are increasingly speculative as we go from cosmic inflation to the mathematical universe hypothesis. But they represent serious attempts by physicists to understand what lies beyond our observable universe and the deepest nature of reality. What lies outside the universe? The answer is, we don't know. But we have theories. And we continue to search for evidence. The universe is stranger and vaster than our ancestors imagined, and our understanding of it continues to evolve. In the 1980s, cosmologists faced a puzzling problem. The Big Bang Theory explained the origin of the universe remarkably well. It matched observations of the cosmic microwave background, the expansion of galaxies, and the abundances of light elements. But it had several problems. First, the universe appeared too uniform. The cosmic microwave background showed the same temperature in all directions, accurate to 1 part in 100,000. But the Big Bang Theory predicted the universe should be lumpy and non-uniform. Why was the universe so smooth? Second, the universe appeared geometrically flat. Measurements showed the total density of matter, and energy was almost exactly at the critical density needed for a flat universe. But the Big Bang Theory predicted the universe should be curved, either open or closed. Why was it so precisely flat? Third, we observe magnetic monopoles in our theories of particle physics, but we never see them in nature. Why are they absent? In 1980, Alan Guth proposed a revolutionary solution: cosmic inflation. Guth's idea was simple but profound. In the extremely early universe, there was a brief period of exponential expansion. During this inflationary epoch, the universe expanded by a factor of at least 10 to the 26th power in a fraction of a second. This enormous expansion had dramatic consequences. First, it stretched any initial lumpiness smooth. Like inflating a balloon removes wrinkles, inflation smoothed out irregularities in the early universe. This explained why the universe is so uniform. Second, it flattened the geometry. Just as the surface of an inflating balloon becomes flatter and flatter, inflation flattened the geometry of the universe. This explained why the universe is so precisely flat. Third, it diluted the density of monopoles and other unwanted relics. They were present but became so sparse they're effectively absent. This explained why we don't observe monopoles. Inflation solved multiple problems at once. It was an elegant theoretical advance, and remarkably, observations soon confirmed it. The cosmic microwave background has tiny temperature fluctuations, 1 part in 100,000. These fluctuations have a specific pattern. Inflation predicts this pattern. The density fluctuations in the early universe get stretched by inflation to become the seeds of galaxies today. The predicted spectrum of density fluctuations matches observations beautifully. Inflation became the dominant theory in cosmology. But Guth's original inflation theory had a problem. It didn't end smoothly. In his theory, inflation was caused by a quantum field called the inflaton field. This field had an energy density that drove exponential expansion. For inflation to end, the inflaton field had to roll down the energy landscape and reach a minimum. But quantum mechanics allows the inflaton field to do something strange. It can tunnel through energy barriers. When you calculate how inflation ends in Guth's theory, you find that the inflaton field tunnels through a barrier and decays rapidly in most regions. This creates a bubble of reheated universe where inflation has ended and normal physics takes over. But the calculation shows something peculiar. Before the field tunnels in a region, inflation continues in the surrounding space. And inflation expands the surrounding space exponentially. So while one bubble stops inflating and becomes a reheated universe, the inflating space around it doubles in volume every instant. The expansion of the surrounding space more than compensates for the bubble that stops inflating. The net result: more inflating space remains after inflation ends than before. This seems paradoxical. How can inflation end if the amount of inflating space keeps growing? In 1986, Andrei Linde realized the answer. Inflation never truly ends. It ends in some regions, creating bubbles of normal universe like ours, but it continues forever in other regions, eternally creating new bubbles. Inflation is eternal. To understand eternal inflation, we need to think carefully about quantum mechanics and the inflaton field. In quantum mechanics, fields are not static. They fluctuate. Even in the vacuum, the lowest energy state, quantum fields jiggle due to quantum uncertainty. These quantum fluctuations have real effects. They create particle-antiparticle pairs that annihilate almost instantly. The inflaton field is no exception. It fluctuates due to quantum effects. Now, during inflation, something remarkable happens. The exponential expansion of space stretches these quantum fluctuations to enormous scales. Typically, quantum fluctuations are microscopic, Planck scale, around 10 to the power of minus 35 meters. But inflation stretches them to macroscopic scales, large enough to become density perturbations that seed galaxies. These stretched quantum fluctuations are crucial. They explain why galaxies exist. But there's another effect of quantum fluctuations during inflation. Sometimes, due to quantum tunneling, a region of space can tunnel from the inflating state, high inflaton field energy, to a state where inflation has ended, low inflaton field energy. This happens randomly in different regions. When it happens, a bubble of non-inflationary space forms. Inside the bubble, the inflaton field is at low energy. Inflation stops. The field reheats the bubble, creating normal matter and radiation. The bubble expands at normal speeds, limited by the speed of light. But outside the bubble, inflation continues, and inflation expands exponentially, much faster than light. So even though a bubble of normal universe forms, the amount of inflating space surrounding it keeps growing. Here's the key insight. Exponential growth always beats linear growth. Inside the bubble, the universe expands at the speed of light. Linear expansion. Outside the bubble, inflation causes exponential expansion. Exponential always wins. Let me illustrate with numbers. Suppose at time zero, a bubble forms with some volume. Outside the bubble, the inflating space doubles in volume every 10 to the power of minus 36 seconds, a typical inflation timescale. Inside the bubble, space expands more slowly. After 100 timescales, the inflating space outside has grown by a factor of 2 to the power of 100, which is about 10 to the power of 30. The bubble has grown by a factor of maybe 100. The inflating space vastly outweighs the bubble. After 1,000 timescales, the inflating space has grown by 2 to the power of 1,000, an unimaginably large number. The bubble has grown maybe 10,000 times. Again, the inflating space dominates. No matter how fast the bubble expands, the inflating space outside expands exponentially faster. The fraction of space that is inflating actually increases over time. This is the fundamental mechanism of eternal inflation. Bubbles form constantly as quantum fluctuations tunnel the inflaton field to lower energies. But exponential inflation in the surrounding space means that more inflating space is created than bubbles are created. Inflation never ends in the global sense. It ends in local regions, the bubbles, but it continues forever in the broader universe. Linde called this the self-reproducing universe. Inflation reproduces itself. It creates the conditions for more inflation. Here's how it works in detail. Imagine we zoom out to look at the universe at very large scales, much larger than our observable universe. At these scales, inflation is happening everywhere. Quantum fluctuations cause the inflaton field to vary from place to place. In regions where the field is higher, inflation proceeds faster. In regions where the field is lower, inflation is slower or has already ended, creating bubbles. The regions of faster inflation expand exponentially faster than regions of slower inflation. So the inflating regions grow to dominate the universe. This creates a kind of natural selection. Regions that can sustain inflation for longer grow to dominate. The universe evolves toward a state where inflation can continue indefinitely. It self-selects for inflation. Moreover, within the inflating regions, quantum fluctuations cause the inflaton field to have random values in different locations. Some of these locations have high inflaton field values, enabling continued rapid inflation. These high field regions expand exponentially and come to dominate, but they contain fluctuations to lower values where new bubbles nucleate. The result? An eternally inflating, self-reproducing universe. Inflation continues forever globally, while locally creating bubbles where it has ended. Each bubble is a universe like ours. What does the structure of an eternally inflating universe look like? Imagine a vast tree growing eternally. The trunk represents the initial inflation that started from the Big Bang. As inflation proceeds, it branches. Some regions continue inflating, others stop, forming bubbles. These bubbles are daughter universes, universes like ours, but the branches that continue inflating don't just stop. They branch again. Quantum fluctuations cause new bubbles to nucleate in the inflating regions. The result is a fractal-like tree structure, eternally growing with infinitely many branches. Each branch corresponds to a region that's still inflating. Each leaf of the tree corresponds to a bubble universe that's stopped inflating. A universe like ours. Because the tree has infinitely many branches, there are infinitely many bubbles. Infinitely many universes. Each bubble universe can have different properties because the inflaton field can have different values in different bubbles. If the inflaton field is rolling down a complex landscape with multiple minima corresponding to different physical laws, then different bubbles can settle into different minima. This is where the connection to string theory comes in. String theory predicts a landscape of possible vacuum states, different minima in the energy landscape. Each minimum corresponds to a different set of physical laws and fundamental constants. Eternal inflation explores this landscape. Different bubbles tunnel to different minima, realizing different possible universes. The result? Infinitely many universes with different physical laws. Here's something remarkable. The tree of eternally inflating space never stops growing. At any given moment in time, there's a definite amount of inflating space and a definite number of bubble universes. But as time advances, more bubbles nucleate. The amount of inflating space increases. The number of bubble universes increases. This continues forever. At every time slice, there are infinitely many bubble universes that have already formed. But there's also infinitely much inflating space remaining, which will form infinitely many more bubbles in the future. The multiverse is not just infinite, it's infinitely growing. There's no final state. The process never reaches completion. This is eternal inflation, the creation of infinitely many universes continuing forever. Eternal inflation raises deep questions about time and causality. In traditional cosmology, we think of time as universal. All events across the universe happen at a common moment in time. But in eternal inflation, this breaks down. Different regions of space inflate at different rates. Causality becomes tangled. Consider an observer in one bubble universe. From their perspective, the Big Bang happened at some time in the past. But from the perspective of an observer in a neighboring bubble that nucleated later, the time of the Big Bang is different. The concept of a universal time doesn't make sense across bubbles. Each bubble has its own time, flowing at its own rate. Moreover, causality becomes peculiar. Events in one bubble can influence whether and when neighboring bubbles nucleate. But events in distant bubbles, causally disconnected, cannot influence each other. The result is a complex causal structure that's hard to visualize. Physicists describe it using eternal time, coordinates. Eternal inflation raises deep questions about time and causality. In traditional cosmology, we think of time as universal. All events across the universe happen at a common moment in time. But in eternal inflation, this breaks down. Different regions of space inflate at different rates. Causality becomes tangled. Consider an observer in one bubble universe. From their perspective, the Big Bang happened at some time in the past. But from the perspective of an observer in a neighboring bubble that nucleated later, the time of the Big Bang is different. The concept of a universal time doesn't make sense across bubbles. Each bubble has its own time, flowing at its own rate. Moreover, causality becomes peculiar. Events in one bubble can influence whether and when neighboring bubbles nucleate, but events in distant bubbles, causally disconnected, cannot influence each other. The result is a complex causal structure that's hard to visualize. Physicists describe it using eternal time coordinates, a mathematical framework that captures the causal structure of eternal inflation. The picture is humbling. From the perspective of eternal time, the Big Bang is not a single event, but an infinite process. Universes bubble off eternally, each with its own time evolution. We live in one bubble. From our perspective, the universe had a beginning, our Big Bang, and will have an end, heat death or some other fate. But globally, across all bubbles, the universe is eternal. Eternal inflation is a theoretical framework, not directly observable. We can't see other bubble universes. They're beyond our cosmic horizon. But eternal inflation makes predictions about our observable universe that we can test. These predictions emerge from the quantum fluctuations that eternal inflation stretches to macroscopic scales. The quantum fluctuations in the inflaton field become density fluctuations, regions of slightly higher and lower density. These density fluctuations seed the formation of galaxies. The pattern of density fluctuations has a specific spectrum. Inflation predicts that smaller scale density fluctuations are more common than larger scale ones. This prediction can be tested by observing the distribution of galaxies and the temperature fluctuations in the cosmic microwave background. Observations of the cosmic microwave background from WMAP and Planck satellites have mapped these temperature fluctuations in exquisite detail. The observed spectrum matches the prediction of inflation remarkably well. This is strong evidence that inflation happened. But can we test eternal inflation specifically? Eternal inflation makes a more specific prediction. The pattern of density fluctuations should be scale invariant with no preferred scale. This is called Harrison-Zeldovich-Peebles scale invariance. Observations show that the spectrum is nearly scale invariant with only small deviations. This matches eternal inflation's predictions, but it also matches some non-eternal inflation models, so the test is not definitive, but it's consistent. A more direct test of eternal inflation would be to look for evidence of collisions with other bubble universes. If our bubble universe collided with a neighboring bubble in the past, it would leave a signature in the cosmic microwave background. The collision would create a circular region of higher or lower temperature. Physicists call this a Brun-Vitos circle. Multiple collisions would create multiple circles. Astronomers have searched for such circles in the Planck satellite data. The search is challenging because we need to look through the entire sky and account for the possibility that circles might be partially outside our observable universe. So far, no definitive circles have been found. But the searches continue, and the techniques are improving. If a collision signature is found, it would be revolutionary evidence for eternal inflation and the multiverse. It would tell us eternal inflation happened. Our bubble collided with another. There are other bubbles beyond our horizon. This would transform multiverse theory from pure speculation to observational science. However, the absence of collision signatures doesn't disprove eternal inflation. Collisions might be rare. Our bubble might not have collided with any others. Or the collisions might have happened outside our observable universe, leaving no signatures we can see. So the non-detection of collision circles doesn't rule out eternal inflation. It just means eternal inflation remains consistent with observations so far. Eternal inflation creates a deep problem for scientific prediction. In a single universe, we can use the laws of physics to predict what should happen. We make measurements, apply the laws, and derive predictions. We test the predictions. If they match observations, the theory is confirmed. But in eternal inflation, there are infinitely many bubbles with potentially different physical laws. Different bubbles can have different values of the fundamental constants. Some bubbles might have constants that allow stars to form and chemistry to work. Life can exist. Other bubbles might have constants that don't allow stars or chemistry. Life cannot exist. So what should we predict about the constants in our bubble? If bubbles are created randomly with all possible constant values equally likely, then we might expect our bubble to have typical constant values. But typical is ill-defined in an infinite multiverse. This is called the prediction problem in eternal inflation. Physicists have proposed several solutions. One approach is to use the anthropic principle. We observe constants that allow life because we exist. We necessarily find ourselves in a bubble capable of supporting life. This doesn't predict what the constants should be, but it explains why we find ourselves in a life-supporting universe. Another approach is to assign probabilities based on the size of regions with different properties. Regions that support inflation longer are larger. Regions that tunnel to life-supporting constants should be weighted by their size. But this runs into technical difficulties. How do you define size in an eternally inflating universe where time is not universal? Different definitions of size give different predictions. This is called the measure problem. Despite decades of work, physicists haven't found a fully satisfactory solution to the measure problem. It remains a major open question in eternal inflation theory. Eternal inflation becomes truly powerful when combined with string theory. String theory predicts a landscape of possible vacuum states, approximately 10 to the power of 500 of them. Each vacuum state corresponds to a different compactification of the 6 extra dimensions and a different set of physical laws. Different vacua have different values of the fundamental constants: the strength of gravity, the electron mass, the fine structure constant, and so on. Alone, string theory just predicts that 10 to the power of 500 possible universes are mathematically consistent. It doesn't explain why our universe has the constants it does, but combine string theory with eternal inflation, and something remarkable happens. Eternal inflation explores the string landscape. Different bubbles tunnel to different vacua. Some bubbles have constants that match vacuum 1. Other bubbles match vacuum 2. Others match vacua 3, 4, 5, up to 10 to the power of 500. Eternal inflation doesn't just create multiple universes. It creates universes realizing different parts of the string landscape. In some bubbles, gravity is very weak. In others, it's strong. In some bubbles, the electron mass is larger. In others, it's smaller. In some bubbles, the fine structure constant, which determines chemistry, is different. Different bubbles realize different possible physics. The result is a multiverse with truly different laws of physics in different regions. This is where eternal inflation connects to the ultimate multiverse picture, infinitely many bubbles exploring the landscape of possible physics. This brings us to one of cosmology's deepest puzzles: fine-tuning. The fundamental constants of physics appear finely tuned for life. If the strength of gravity were slightly weaker, stars wouldn't form. No chemistry, no life. If it were slightly stronger, stars would burn out too quickly. Again, no life. The electron mass must be within a narrow range for chemistry to work. The fine structure constant must be in a specific range for atoms to be stable. The cosmological constant must be incredibly small, 120 orders of magnitude smaller than particle physics predicts, for the universe to expand slowly enough for galaxies to form. List after list of constants appear finely tuned for life. The old view: this is just coincidence. We're lucky. But eternal inflation and string theory suggest another possibility. If there are 10 to the power of 500 possible universes, each with different constants, then we'd expect to find ourselves in one of the rare universes with life-supporting constants. This is the anthropic explanation. We observe life-supporting constants because we exist. We couldn't observe non-life supporting constants because no observers would exist to make observations. This is sometimes called the weak anthropic principle. Before eternal inflation, this seemed like cop-out physics. We're here because we're here. But eternal inflation makes it concrete. There really are other universes, in theory. And they really do have different constants, according to string theory. So anthropic reasoning becomes legitimate physics. We don't predict the constants, but we explain why we find ourselves observing life-supporting values. Not everyone accepts this reasoning. Some physicists argue it's not truly scientific, but many have embraced it as a way to make sense of fine-tuning in the context of eternal inflation and the string landscape. To understand eternal inflation in detail, we need to understand how bubbles actually form. Bubbles form through a process called bubble nucleation. This involves quantum tunneling, one of quantum mechanics' strangest phenomena. In classical mechanics, if you have a ball in a valley with a hill in the way, the ball stays in the valley. It can't climb the hill without enough energy to do so. But in quantum mechanics, the ball can tunnel through the hill. There's a probability that the ball will appear on the other side of the hill, even though it didn't have enough energy to climb over. The probability depends on the height and width of the hill and the energy of the particle. High, wide hills are hard to tunnel through. Low, narrow hills are easy. Something similar happens with the inflaton field during eternal inflation. The inflaton field can exist in different states, corresponding to different energy densities. The high energy state, high inflaton field value, corresponds to inflation. Space expands exponentially. The low energy state, low inflaton field value, corresponds to non-inflationary space. Inflation has ended. Separating these states is an energy barrier, like the hill in the quantum tunneling analogy. During inflation, quantum tunneling can cause the inflaton field to tunnel through this barrier. When it does, a region of space transitions from the high energy inflating state to the low energy non-inflating state. This is bubble nucleation. The high energy state is called a false vacuum because it's not the true lowest energy state. The low energy state is the true vacuum. The field tunnels from the false vacuum to the true vacuum, nucleating a bubble of true vacuum space. How often do bubbles nucleate? This depends on the quantum tunneling probability. Physicists use semi-classical approximation to calculate the tunneling rate. The result is that the nucleation rate depends exponentially on the height and width of the energy barrier. Specifically, the nucleation probability per unit volume per unit time is gamma is proportional to E to the power of minus B over h bar, where B is a quantity called the bounce action, a measure of the barrier height and width. If B is large, the nucleation rate is exponentially suppressed. Tunneling is rare. If B is small, the nucleation rate is high. Tunneling is common. Here's the crucial point. Even if tunneling is very rare, it happens eventually. During the exponential expansion of inflation, the volume of space grows exponentially. The probability of at least one bubble nucleating. How often do bubbles nucleate? This depends on the quantum tunneling probability. Physicists use semi-classical approximation to calculate the tunneling rate. The result is that the nucleation rate depends exponentially on the height and width of the energy barrier. Specifically, the nucleation probability per unit volume per unit time is gamma is proportional to E to the power of minus B over h bar, where B is a quantity called the bounce action, a measure of the barrier height and width. If B is large, the nucleation rate is exponentially suppressed. Tunneling is rare. If B is small, the nucleation rate is high. Tunneling is common. Here's the crucial point. Even if tunneling is very rare, it happens eventually. During the exponential expansion of inflation, the volume of space grows exponentially. The probability of at least one bubble nucleating in a given time interval is approximately p approximately equals 1 minus exp minus gamma times v times delta t, where v is the volume of space and delta t is the time interval. Because v grows exponentially with time during inflation, even if gamma is tiny, eventually the product gamma times v becomes large. When gamma times 5 times delta t is much greater than 1, bubble nucleation becomes probable. The time until the first bubble nucleates is roughly Tu is approximately 1 over open parenthesis, gamma times v 0 times xp open parenthesis 3, ho, close parenthesis, where v0 is an initial volume, that h is the inflation rate, and t is time. The exponential factor A3 in the denominator shows that the volume grows exponentially, making bubble nucleation increasingly likely. Eventually, bubbles nucleate. Once the first bubble forms, it doesn't stop further bubble nucleation. The inflating space outside the bubble continues to expand exponentially. New bubbles form at a rate that increases with time. The result? Infinite bubbles nucleate in infinite time. What happens inside a newly nucleated bubble? When a bubble forms, the inflatoned field has tunneled to the true vacuum, a low energy state. But the field doesn't instantly settle to this minimum. It oscillates around the minimum. These oscillations convert the potential energy of the field into radiation and matter. The process is called reheating. During reheating, the energy density of the inflaton field is converted into a hot plasma of particles, quarks, gluons, leptons, photons, all in thermal equilibrium. The temperature of this plasma depends on how much energy is available. For typical inflation models, the reheating temperature is around 10 to the power of 9 to 10 to the power of 16 Kelvin. This is hot enough that the standard model of particle physics applies. Once reheating is complete, the bubble contains a hot universe full of elementary particles. This is effectively the initial state of our Big Bang. From the perspective of an observer inside the bubble's initial state is a Big Bang. The universe was infinitely hot and dense, or nearly so before quantum gravity effects become important. It expands and cools. The standard cosmology follows. The first 3 minutes of nucleosynthesis, the era of recombination, the cosmic dark ages, the formation of galaxies, stars, and eventually observers like us. But from the perspective of an external observer outside the bubble, watching from the eternally inflating space, something different is happening. The bubble expands at nearly the speed of light. The inflating space outside continues to expand exponentially. The bubble's expansion slows relative to the exponential expansion outside. From the external perspective, the bubble's relative size decreases over time. This is a key asymmetry. Observers inside the bubble and observers outside see very different pictures. Let's think carefully about what it means for a bubble universe to form. From the external perspective, a bubble nucleates at a specific point in the eternally inflating space. It expands rapidly but subluminally, slower than light. As it expands, the inflaton field inside continues to oscillate and reheat. After a brief period, nanoseconds to microseconds, the bubble contains a hot, uniform plasma in thermal equilibrium. This is the beginning of the bubble's universe. But here's something profound. The Big Bang of the bubble is not the same as the Big Bang of the parent inflation. The parent inflation goes back to the true Big Bang, the origin of the universe. But the bubble's Big Bang is a local event, happening billions of years later, in parent time. The bubble is born inside the eternally inflating space, not at the origin of time. From the perspective of observers inside the bubble, they look back and infer a Big Bang at x equals 0 in their time coordinate. They measure radiation coming from all directions and infer a hot, dense past. They're right about the local history of their bubble, but they're not seeing the true origin of all universes. That's hidden beyond their cosmic horizon. The eternal inflation and the parent universe are beyond their observable universe. This raises a profound point. Observers in any bubble universe will infer a Big Bang, even though the bubble is actually born inside an eternally inflating space, billions of years after the original Big Bang. The Big Bang is not a single cosmic event that gave birth to all existence. It's a local event in each bubble, marking the beginning of that bubble's observable universe. This is a radical shift from traditional cosmology. What happens if two bubbles nucleate nearby and expand toward each other? Eventually, they collide. A collision between bubbles is a dramatic event. The boundary between the two bubbles is the domain wall between two different vacuum states. When the bubbles collide, the domain wall separates them, moving at nearly the speed of light. The collision releases energy in the form of gravitational waves and particle production. From inside each bubble, the collision appears as a violent event, potentially creating a shock wave or heating the matter in the collision region. If the two bubbles have different physical laws, the collision is even more dramatic. At the collision boundary, the physical constants must change from one set to another. Particles might not be able to cross the boundary. Forces might be discontinuous. The collision dynamics are complex and not fully understood. After the collision, the bubbles merge. The domain wall between them gradually dissipates or evaporates. If the bubbles have similar energy densities, they merge relatively smoothly. If they have very different energy densities, the dynamics are chaotic. The implications are interesting. If our universe collided with another bubble in its past, that collision would have left imprints. It might have created primordial gravitational waves. It might have produced topological defects, domain walls, cosmic strings, monopoles. The collision might have created regions of high temperature or pressure that left signatures in the microwave background. Astronomers have searched for collision signatures without definitive results so far, but the possibility remains. Our universe might bear the scars of a collision with another bubble. That collision would be direct evidence of eternal inflation and the multiverse. One of the deepest problems in eternal inflation is the measure problem. In a finite universe, probability is straightforward. If I have a bag with 100 red balls and 50 blue balls, the probability of drawing a red ball is 100 over 150 equals 2/3. I'm dividing the number of red balls by the total number of balls. But in an eternally inflating universe with infinitely many bubbles, this breaks down. How do you compute probabilities when there are infinitely many bubbles of different types? The total number of bubbles is infinite. The number of each type of bubble might also be infinite. The ratio infinity over infinity is undefined. So how do we assign probabilities? Different physicists have proposed different solutions called measures. One measure is the proper time measure. It weights each bubble by the total proper time, the time experienced by observers inside the bubble that elapses before the bubble nucleates. Bubbles that nucleate late, in external time, are weighted more heavily. This approach gives well-defined probabilities but has the strange feature that observers who live longer, in external time, are counted more heavily. Another measure is the volume weighting. It weights each bubble by the volume of inflating space it occupies at a given time. But volume is ambiguous in an eternally inflating space. There's no universal time. Different definitions of volume give different probability distributions. A third measure is the scale factor cutoff. It counts the number of bubbles as a function of the expansion factor of the parent inflation. But this also has ambiguities about how to handle the infinite volume. A fourth is the light cone time measure, which uses the proper time measured along light cones. Each measure gives a different prediction for the probabilities of different bubble types. And here's the problem: we don't know which measure is correct. The measures are not equivalent. They make different predictions about the relative frequencies of different universe types. If one measure predicts that life-supporting universes are common, another might predict they're rare. Without knowing the correct measure, we can't make definite predictions about the probability distribution of bubble properties. This is the measure problem, and it remains unsolved. The measure problem leads to a puzzling prediction: the youngness paradox. Consider the probability distribution of the age of the universe in the ensemble of all bubbles. Naively, you might expect older bubbles to be more common than younger ones. Older bubbles have had more time to form, so there should be more of them. But in eternal inflation, this reasoning is wrong. The fraction of bubbles that are younger than time t actually increases as t increases. More bubbles nucleate at late times than at early times. This is because the volume of the inflating space grows exponentially. As the volume grows, more bubbles nucleate, so later times have more bubble nucleations. The fraction of bubbles younger than time t is p age less than t, approximately equals 1 minus xp minus gamma times vt times t. For large t, vt grows exponentially, so p age less than t approaches 1. Almost all bubbles are younger than any given time scale. This seems paradoxical. If almost all bubbles are young, shouldn't we expect to observe ourselves in a young universe? Our universe's age is about 13.8 billion years. But if most bubbles are much younger, we'd expect to find ourselves in a universe less than 1 billion years old. Yet we don't. This is the youngness paradox, or Boltzmann brain paradox. One resolution involves the anthropic principle. We can only observe ourselves in bubbles old enough for observers to have formed. Observers require stars to form, which requires billions of years. So we necessarily find ourselves in a relatively old bubble, even if young bubbles are more common in the ensemble. But this resolution requires anthropic reasoning, which is controversial. Some physicists argue the paradox points to a fundamental problem with eternal inflation. Others argue it's resolved by carefully choosing the correct measure. The youngness paradox remains an active area of research. Is eternal inflation scientifically testable? This is a contentious question. On one hand, eternal inflation makes predictions about our observable universe. We've discussed how it predicts scale invariant density fluctuations, which match CMB observations. It predicts that certain topological defects are diluted, which is observed. These predictions support eternal inflation. On the other hand, eternal inflation also makes predictions that we can't directly test. We can't see other bubbles. They're beyond our cosmic horizon. We can't directly verify that infinitely many universes exist. We can't directly measure the properties of the string landscape. Some physicists argue this makes eternal inflation non-scientific. Falsifiability is a hallmark of science. A theory should make predictions that can be tested or falsified. Is eternal inflation scientifically testable? This is a contentious question. On one hand, eternal inflation makes predictions about our observable universe. We've discussed how it predicts scale invariant density fluctuations, which match CMB observations. It predicts that certain topological defects are diluted, which is observed. These predictions support eternal inflation. On the other hand, eternal inflation also makes predictions that we can't directly test. We can't see other bubbles. They're beyond our cosmic horizon. We can't directly verify that infinitely many universes exist. We can't directly measure the properties of the string landscape. Some physicists argue this makes eternal inflation non-scientific. Falsifiability is a hallmark of science. A theory should make predictions that can be tested or falsified. If a theory makes no testable predictions, it's not science. It's metaphysics or philosophy. From this perspective, eternal inflation is untestable and therefore not science. Proponents of eternal inflation counter that the theory makes testable predictions about the CMB, galaxy distribution, and other observable phenomena. The fact that the theory also predicts unobservable things, other bubbles, doesn't make it unscientific. Many successful theories predict unobservable entities, the interior of black holes, the far future universe, quantum fields in the vacuum. We accept these as scientific despite not being directly observable. Similarly, eternal inflation is scientific because it makes testable predictions about observable phenomena, even though it also predicts unobservable universes. This debate remains unresolved in the physics community. Some leading physicists like Roger Penrose argue eternal inflation is not genuinely scientific. Others, like Alan Guth and Andre Linde, defend it as good physics. The status of eternal inflation as science depends on how we define testability and falsifiability. Since Linde's original proposal, theorists have developed many refinements and variations of eternal inflation. One important variation is slow-roll eternal inflation. In slow-roll models, the inflaton field rolls slowly down a gentle potential. This sustains inflation for a long time, but eventually ends. Eternal inflation occurs because quantum fluctuations can kick the field back up the potential, sustaining inflation in some regions while it ends in others. Another variation is hybrid inflation, In hybrid models, there are two scalar fields. One field, the inflaton, is small and nearly frozen. Another field, the waterfall field, drives inflation. When the inflaton reaches a critical value, the waterfall field rapidly transitions, ending inflation. But quantum fluctuations can prevent the waterfall in some regions, sustaining eternal inflation. String theory inflation provides another framework. In string theory, inflation is driven by the motion of branes in higher dimensional spaces or by other string theoretic mechanisms. String inflation models naturally incorporate the landscape of vacua, making eternal inflation a generic prediction. Stochastic inflation is a mathematical framework that treats the inflaton field as a stochastic, random variable during inflation. This approach quantifies the randomness of quantum fluctuations and makes precise predictions about eternal inflation. Each of these variations predicts eternal inflation, but with different details and different consequences for the multiverse. Some variations predict that different bubbles have wildly different properties. Others predict that bubble properties are more correlated. The diversity of eternal inflation models reflects the breadth of the theoretical landscape. One fundamental challenge to eternal inflation comes from quantum gravity. Eternal inflation relies on semi-classical calculations, treating gravity classically while quantum fields fluctuate. But at sufficiently early times or high densities, quantum gravity effects become important. Quantum gravity is the regime where both space-time geometry and quantum mechanics are fully quantum. The theory of quantum gravity is not yet well understood. We have promising candidates like string theory and loop quantum gravity, but no consensus. In quantum gravity, the concept of space-time itself might break down. If space-time is not fundamental but emerges from some deeper structure, then eternal inflation's picture of bubbles nucleating in a classical space-time background might be incomplete or incorrect. Quantum gravity might eliminate the distinction between different bubble universes, or it might predict that eternally inflating space is unstable and decays. Or it might show that the semi-classical calculations used to derive eternal inflation are invalid at the relevant scales. None of this is certain. Quantum gravity is speculative, but it's a reminder that eternal inflation, like all quantum field theory in curved spacetime, is an effective theory valid at intermediate scales. At the deepest level, the Planck scale, new physics emerges. That new physics might vindicate eternal inflation or might overturn it entirely. Understanding how eternal inflation emerges from quantum gravity is one of the major open challenges. Chaotic inflation, proposed by André Linde in 1986, is one of the earliest and most elegant models of eternal inflation. In chaotic inflation, the inflaton potential is very simple. V of phi equals lambda phi to the power of n, where lambda is a coupling constant and n is an integer. Typically, n equals 2 or 4. This potential looks like a parabola or quartic curve. During inflation, the inflaton field rolls down this potential, losing energy and slowing down. Because the field rolls slowly, the deceleration is gradual. This sustains inflation for a long time. But quantum fluctuations constantly jiggle the field, sometimes pushing it back up the potential. In some regions, quantum fluctuations overcome the rolling motion, and the field moves back up. These regions continue to inflate. In other regions, the field rolls to the minimum and inflation stops. The result: eternal inflation in the regions where quantum fluctuations dominate. Chaotic inflation is elegant because it doesn't require a complex potential with multiple minima. A simple, smooth potential naturally produces eternal inflation. Moreover, chaotic inflation was one of the first models to make detailed predictions about density fluctuations. These predictions match CMB observations remarkably well. For this reason, chaotic inflation remains one of the most studied eternal inflation models. When bubbles nucleate in eternal inflation, they're separated by domain walls, boundaries where the inflatoned field transitions from high values to low values. These domain walls are topological defects. They're extended objects, two-dimensional surfaces in three-dimensional space, that persist as long as the bubbles are separated. Domain walls have several important properties. First, they carry energy density. The inflatoned field has different values on either side of the wall, so there's a potential energy difference. This energy is localized at the wall. Second, domain walls exert pressure. They tend to move and expand due to their surface tension. The pressure is outward, away from the wall. Third, domain walls can annihilate if they meet other walls with opposite orientations, or they can repel if they have the same orientation. When bubbles collide, their domain walls interact. If two bubbles are in vacuum states that oppose each other across a potential barrier, the colliding domain wall is unstable. It radiates energy and can decay into particle pairs. The decay releases gravitational waves and produces a shower of particles. This has implications for observational signatures. If our universe collided with another in its past, the collision would have produced gravitational waves. Modern gravitational wave detectors like LIGO are sensitive to certain frequency ranges, but not others. Future detectors might be able to detect primordial gravitational waves from bubble collisions. Domain walls also affect cosmological evolution. If domain walls persist in the universe after bubble collisions, they're a form of exotic matter. Observations of the universe place constraints on the abundance of domain walls. These constraints limit which eternal inflation models are viable. Some variations of eternal inflation involve extra dimensions and brane worlds. The Randall-Sundrum scenario proposed by Lisa Randall and Raman Sundrum is one example. In this scenario, our universe is a three-dimensional brane embedded in a higher dimensional space. The bulk. We live on the brane. Forces like electromagnetism and the nuclear forces are confined to the brane. Only gravity can leak into the bulk. This explains why gravity appears so weak compared to other forces. Gravity's strength is diluted by spreading into extra dimensions. In the Randall-Sundrum context, eternal inflation can occur in the bulk. Bubbles nucleate in the four-dimensional bulk and expand. If a bubble nucleates near our brane, it might interact with our brane. This could produce observable effects, cosmic strings, gravitational wave pulses, or particle showers. Another variation involves multiple branes. If there are many branes in the bulk, bubbles nucleating in the bulk could collide with different branes. Each collision creates a universe on that brane. The result? Eternally inflating bulk with multiple branes, each hosting its own universe. These brane world scenarios extend eternal inflation beyond the classical picture. They incorporate extra dimensions and suggest that eternally inflating space might have a rich, multifaceted structure. However, brane world models require extra dimensions, which have no observational evidence. They remain speculative. Most eternal inflation models use scalar fields, fields with a single value at each point in space. But theorists have explored eternal inflation with other types of fields. Vector inflation uses vector fields, fields with direction and magnitude like electric fields. Vector fields can drive inflation through different mechanisms than scalar fields. They allow for more exotic inflation dynamics. Tensor inflation uses tensor fields, fields with multiple components arranged in a matrix form. These allow for even more complex dynamics. Hybrid models combine multiple field types. For example, one field might drive inflation, while another field determines when inflation ends. The interplay between the fields can create rich eternal inflation phenomenology. Why explore these exotic models? First, they might better match observations. Some models fit the CMB data better than simple scalar models. Second, they emerge naturally from string theory. String theory contains many types of fields, and inflation might use these fields. Third, they make different predictions about the multiverse. Different field types in eternal inflations can produce bubbles with different characteristics. The inflationary parameter space is vast. As observational constraints improve, some models are ruled out while others gain favor. The diversity of eternal inflation models reflects the depth of the theoretical landscape. Eternal inflation raises profound questions about infinity. The theory predicts infinitely many bubble universes, created over infinite time. Infinity is a concept that humans find difficult to grasp. Our intuitions are built on finite experiences. We understand large numbers, millions, billions, trillions, but infinity is categorically different. It's not just a very large number. When we say infinitely many universes, we need to be careful about what we mean. Do we mean uncountably infinite, like the real numbers, or countably infinite, like the integers? In eternal inflation, the number of bubbles is countably infinite. We can enumerate them in principle: bubble 1, bubble 2, bubble 3, etc. But even countable infinity is strange. Here are some paradoxes infinity creates. Paradox 1, infinity minus infinity. In eternal inflation, infinitely many bubbles form from infinitely much inflating space. If we ask, what fraction of space is in bubbles versus still inflating? The answer is undefined. We're dividing infinity by infinity. Different ways of computing the fraction give different answers. Paradox 2, infinity plus. Infinity, if we have infinitely many bubbles, each with infinitely many atoms, how many atoms total? Is it Aleph 0, countably infinite, or 2 to the power of Aleph 0, uncountably infinite? The answer depends on how we count. Eternal inflation raises profound questions about infinity. The theory predicts infinitely many bubble universes created over infinite time. Infinity is a concept that humans find difficult to grasp. Our intuitions are built on finite experiences. We understand large numbers, millions, billions, trillions. But infinity is categorically different. It's not just a very large number. When we say infinitely many universes, we need to be careful about what we mean. Do we mean uncountably infinite, like the real numbers, or countably infinite, like the integers? In eternal inflation, the number of bubbles is countably infinite. We can enumerate them in principle: bubble 1, bubble 2, bubble 3, etc. But even countable infinity is strange. Here are some paradoxes infinity creates. Paradox 1, infinity minus infinity. In eternal inflation, infinitely many bubbles form from infinitely much inflating space. If we ask, what fraction of space is in bubbles versus still inflating? The answer is undefined. We're dividing infinity by infinity. Different ways of computing the fraction give different answers. This is related to the measure problem we discussed earlier. Paradox 2, infinity plus infinity. If we have infinitely many bubbles, each with infinitely many atoms, how many atoms total? Is it Aleph 0, countably infinite, or 2 to the power of Aleph 0, uncountably infinite? The answer depends on how we count. Paradox 3, the hotel infinity problem. Imagine a hotel with infinitely many rooms, all occupied. A new guest arrives. Can the manager fit them in? Yes. Move guest 1 to room 2, guest 2 to room 3, etc. The new guest takes room 1. All rooms are still full, and the new guest is accommodated. This is how eternal inflation works. Infinitely many bubbles already exist, but new bubbles continuously form. The infinities don't overflow. They just shift. Paradox 4. 2 infinities are better than 1. If we have infinitely many universes, some of which contain infinitely many copies of you, how many yous are there? Are you special? Are all your copies equally real? The infinity of copies makes questions of identity and individuality philosophically problematic. These paradoxes aren't resolved by eternal inflation. They're inherent to any infinitely large system. But they illustrate the philosophical challenges the multiverse raises. Eternal inflation raises questions about determinism and randomness. In quantum mechanics, events are probabilistic. The Schrödinger equation is deterministic. Given the initial state, it predicts how the wave function evolves. But measurement outcomes are random. When we measure a quantum system, we get a random outcome with probabilities given by the Born rule. This randomness is fundamental. It's not due to hidden variables or our ignorance. Eternal inflation is fundamentally random. Quantum fluctuations randomly determine where bubbles nucleate. The tunneling probability determines which vacuum each bubble transitions to. Different bubbles form with different properties, all determined by random quantum events. This raises a profound question. If the universe's properties are determined by random quantum events in eternal inflation, in what sense is the universe determined? One perspective, the entire multiverse consisting of infinitely many bubbles with all possible properties is determined. The Schrödinger equation deterministically evolves the wave function describing all bubbles. From this perspective, determinism is preserved. Everything that can happen does happen. Randomness is just our ignorance of which bubble we inhabit. Another perspective, quantum mechanics is genuinely indeterministic at the fundamental level. The Schrödinger equation describes possibilities, not actualities. Actual outcomes are random. In this case, the multiverse's contents are genuinely random, not determined. Neither perspective is definitively correct. This is a matter of interpretation in quantum mechanics. But eternal inflation makes the debate concrete. If infinitely many bubbles actually exist, each with different properties, then the question, which universe do we inhabit, becomes pressing. And the answer seems to be, we inhabit one of infinitely many selected randomly, or by anthropic selection. This has implications for free will. If our universe's properties, including the laws of physics, are determined by random quantum events in eternal inflation, are our choices free? Some argue that randomness is incompatible with free will. If our choices are random quantum events, they're not ours. Others argue that randomness is necessary for freedom. If everything were determined by prior causes, we'd have no freedom either. Eternal inflation doesn't resolve these ancient philosophical debates, but it makes them unavoidable for anyone thinking seriously about cosmology. The anthropic principle has two forms. The weak anthropic principle states, we must find ourselves in a universe compatible with our existence. We observe life-supporting physical laws and constants because if they were different, we wouldn't be here to observe them. The strong anthropic principle states, the universe must have properties that allow life to develop within it. This is a stronger claim, not just that we find ourselves in a life-supporting universe, but that all universes must be life-supporting. The weak principle is uncontroversial. It's logically trivial. If we exist, we must be in a universe compatible with existence. The strong principle is metaphysical. It suggests a deep connection between the structure of the universe and the existence of observers. Eternal inflation makes the weak principle relevant in a new way. In eternal inflation, infinitely many bubbles form with different properties. Some bubbles have constants that allow stars, galaxies, and life. Others have constants that don't allow complex structures. Observers necessarily find themselves in life-supporting bubbles. So anthropic reasoning explains why we observe life-supporting constants. We're not saying the universe was designed for life. We're saying life can only arise in certain types of universes. We observe ourselves to be in one of those types. This is reasonable, but it has a strange implication. Our observations don't directly constrain the properties of the multiverse. Instead, they constrain the subset of the multiverse we can inhabit. Different bubbles might have properties inconsistent with observers. We'd never know because we can't be in those bubbles. This is sometimes called observer selection bias. Some physicists argue this is a valid use of the anthropic principle in cosmology. Others argue it's a cop-out. If we can't make falsifiable predictions because we must be in a life-supporting bubble anyway, how is the theory testable? This debate is unresolved. But eternal inflation makes anthropic reasoning inescapable. In a single universe, probability is clear. If I flip a coin, there's a 50% chance of heads. I can repeat the experiment many times and verify the probability. But in an eternally inflating multiverse, probability becomes murky. Each bubble forms once. There's no ensemble of similar experiments to average over. So what does it mean to say there's a 30% probability that a bubble has certain properties? One interpretation: the probability is objective. It's the fraction of bubbles with that property in the multiverse. But as we discussed with the measure problem, there's no unique way to define fraction of infinitely many bubbles. Another interpretation: the probability is epistemic. It represents our ignorance. We don't know which bubble we inhabit, so we assign probabilities based on principles like the anthropic principle. From this perspective, probability is about our state of knowledge, not an objective property of the multiverse. A third interpretation: probability is related to what we can observe. If bubble properties are distributed in a certain way, and we're a random observer in a random bubble, then we can make probabilistic predictions about what we should observe. This is sometimes called the self-sampling assumption or self-indication assumption. Each interpretation has strengths and weaknesses. The objective interpretation requires solving the measure problem. The epistemic interpretation seems to make probability subjective. The observer-based interpretation requires defining what random means for observers in different bubbles. Fundamentally, the multiverse challenges our understanding of probability. Probability arose as a framework for analyzing random events in a finite, repeatable context. The multiverse, infinite, unrepeatable, with no external ensemble, doesn't fit this framework. Understanding probability in the multiverse remains an open philosophical and mathematical problem. Eternal inflation and the multiverse raise a philosophical question. Does this expand or diminish our sense of wonder? One perspective: eternal inflation reduces wonder. Before, we thought the universe had a definite beginning and end. The Big Bang was a unique, singular event. The laws of physics were fixed and special. Eternal inflation suggests the opposite. The Big Bang is just a local event in one bubble. Before it are infinitely many other universes. The laws of physics are not unique. Infinitely many other universes have different laws. We're not special. Our universe is one of infinitely many, with no preferred status. This can feel diminishing. We're small, insignificant, lost in an infinite sea of other worlds. Our cosmic importance is reduced to nothing. Another perspective, eternal inflation expands wonder. We thought the universe was finite and comprehensible in principle. Eternal inflation reveals it's infinite and incomprehensibly vast. Instead of one set of physical laws, there are 10 to the power of 500 possible sets, realized in different bubbles. The structure of reality is far richer than we imagined. The emergence of infinite complexity from simple quantum mechanics is astounding. The self-reproducing nature of inflation, universes creating more universes, is genuinely marvelous. Instead of reducing wonder, it relocates it. We move from wondering about the distant stars to wondering about the infinite multiverse. Personally, I think both perspectives have merit. Eternal inflation is humbling. We're a small part of an infinite universe, but it's also wondrous. The universe is incomparably richer and more complex than we once thought. Perhaps the right response is a mixture of humility and awe. Humility because we're infinitesimal in a multiverse. Awe because the multiverse is so much grander than we could have imagined. Eternal inflation raises questions that border on theology. Some theologians and philosophers have engaged with these questions seriously. The problem of divine creation. Traditional theology holds that God created the universe. But if the universe is eternal, without beginning or end, what does creation mean? Some theologians argue eternal inflation is consistent with creation. God could have created the eternal inflation process itself, even if the process has no temporal beginning. Others argue eternal inflation challenges theology. If the universe is fully natural, particles, fields, quantum mechanics, and needs no creator, what role is there for God? Different theistic traditions respond differently. The principle of plenitude. The principle of plenitude from medieval philosophy holds that all possible things actually exist. The multiverse is a modern realization of this ancient principle. If all possible universes exist, as eternal inflation suggests, then existence is maximally full. Nothing possible is left unrealized. Some see this as religiously significant. The multiverse is the most perfect form of existence, all possibilities actualized. Others see it as contrary to traditional monotheism. If everything possible exists, where is the special status of God's creation? Fine-tuning and divine action. Fine-tuning, the apparent design of physical constants for life, has been used as evidence for God. But eternal inflation offers a naturalistic explanation. In an infinite multiverse, some bubbles will have life-supporting constants by chance alone, no designer needed. This undermines the fine-tuning argument for God. Some theologians accept this. They argue that God could work through natural processes like eternal inflation. Natural explanation and divine creation are not mutually exclusive. Others argue that eternal inflation, while scientifically possible, is philosophically problematic. Positing infinitely many unobservable universes to explain fine eternal inflation raises questions that border on theology. Some theologians and philosophers have engaged with these questions seriously. The problem of divine creation. Traditional theology holds that God created the universe. But if the universe is eternal, without beginning or end, what does creation mean? Some theologians argue eternal inflation is consistent with creation. God could have created the eternal inflation process itself, even if the process has no temporal beginning. Others argue eternal inflation challenges theology. If the universe is fully natural, particles, fields, quantum mechanics, and needs no creator, what role is there for God? Different theistic traditions respond differently. The principle of plenitude. The principle of plenitude from medieval philosophy holds that all possible things actually exist. The multiverse is a modern realization of this ancient principle. If all possible universes exist, as eternal inflation suggests, then existence is maximally full. Nothing possible is left unrealized. Some see this as religiously significant. The multiverse is the most perfect form of existence, all possibilities actualized. Others see it as contrary to traditional monotheism. If everything possible exists, where is the special status of God's creation? Fine-tuning and divine action. Fine-tuning, the apparent design of physical constants for life, has been used as evidence for God, but eternal inflation offers a naturalistic explanation. In an infinite multiverse, some bubbles will have life-supporting constants by chance alone. No designer needed. This undermines the fine-tuning argument for God. Some theologians accept this. They argue that God could work through natural processes like eternal inflation. Natural explanation and divine creation are not mutually exclusive. Others argue that eternal inflation, while scientifically possible, is philosophically problematic. Positing infinitely many unobservable universes to explain fine-tuning might be worse than accepting fine-tuning as evidence for design. This is a matter of philosophical judgment. The question of ultimate explanation. Eternal inflation raises the deepest question: why is there something rather than nothing? Traditional theology answers, God is the ultimate explanation. God necessarily exists and creates everything else. Eternal inflation suggests a different answer. The multiverse is the ultimate explanation. Quantum mechanics, vacuum energy, and the inflaton field necessarily exist. They naturally produce eternal inflation and the multiverse. But this raises a further question. Why do quantum mechanics and the inflaton field exist? Why do these laws hold? Does eternal inflation really explain why there's something rather than nothing? Or does it just push the question back a level? Different physicists and philosophers answer differently. Some argue eternal inflation is the deepest explanation we can give. The laws of physics are fundamental. We can't explain why they exist. Others argue eternal inflation leaves the ultimate question unanswered. A complete answer requires explaining why the laws of physics themselves exist. This might require theology, philosophy, or a deeper physics we haven't discovered. These questions transcend science. They're philosophical and theological. But eternal inflation makes them urgent. What does current observational data tell us about eternal inflation? The primary source of evidence is the cosmic microwave background, the radiation left over from the Big Bang. Observations from WMAP 2001 to 2010 and Planck 2009 to 2018 have mapped the CMB with extraordinary precision. The data reveals 1. Nearly scale invariant spectrum. The density fluctuations that seed galaxy formation have a nearly scale invariant spectrum. This matches the prediction of inflation, including eternal inflation. The spectral index n sub s is measured to be approximately 0.96, very close to the scale invariant value of 1. This is strong evidence for inflation. 2. Small tensor modes. Inflation predicts primordial gravitational waves, called tensor modes. These leave a signature in the CMB polarization. Current data constrains the tensor to scalar ratio R to be less than about 0.1. This is consistent with many inflation models, including eternal inflation. 3. No obvious bubble collision signatures. Searches for circular patterns in the CMB that would indicate bubble collisions have found no definitive evidence. Some early claims were retracted after more careful analysis. This is consistent with no collisions in our past, or collisions beyond the observable universe. 4. Gaussian fluctuations. The CMB temperature fluctuations are approximately Gaussian, normal distribution. This is consistent with the predictions of inflation from quantum fluctuations, no evidence for non-Gaussian signals that some exotic models predict. Overall assessment, the CMB data strongly supports inflation, but doesn't uniquely distinguish eternal inflation from other inflation models. Many different inflation models, including eternal and non-eternal versions, fit the data well. To distinguish eternal inflation from alternatives, we'd need detection of primordial gravitational waves, constrains the inflation scale, detection of primordial magnetic fields, observational signatures of bubble collisions, constraints on the spectrum of density fluctuations at very large scales. Future observations might provide these constraints. Eternal inflation is deeply connected to string theory and the search for quantum gravity. String theory provides the landscape, the 10 to the power of 500 possible vacuum states. This landscape is what makes eternal inflation's prediction of different bubble universes with different laws physically plausible. Without string theory's landscape, eternal inflation would create bubbles with the same laws everywhere. But string theory also raises challenges for eternal inflation. One issue is stability. String theory vacua are notoriously unstable. Many vacua decay rapidly through tunneling. If string theory vacua are too unstable, they can't persist long enough for eternal inflation to occur and bubbles to form. This requires careful study of the string landscape stability. Another issue is moduli. String theory involves many scalar fields called moduli, which parameterize the shape of extra dimensions. These moduli couple to the inflaton field. Their dynamics can interfere with inflation and eternal inflation. Understanding how moduli affect eternal inflation is an active research area. Quantum gravity constraints loop. Quantum gravity, another approach to quantum gravity, makes different predictions about the early universe. Some loop quantum gravity models suggest the universe bounced before the Big Bang, rather than starting at a singularity. If this is correct, eternal inflation might not apply to the far past. Other quantum gravity approaches, like asymptotic safety, suggest the universe is asymptotically free at high energies. This could affect inflation dynamics at very early times. Reconciling eternal inflation with quantum gravity is one of the major challenges facing cosmology. The theory must be consistent with whatever quantum gravity turns out to be correct. Several future observations and experiments could test eternal inflation or constrain it. Next generation CMB experiments. Projects like CMB-S4, CMB Stage 4, will measure the CMB with unprecedented sensitivity. They aim to detect primordial gravitational waves and constrain the tensor to scalar ratio to an accuracy of R approximately 0.001. This would provide strong constraints on inflation models. If primordial gravitational waves are detected, it would confirm that inflation occurred at high energy scales. Gravitational wave detectors. Advanced LIGO and future detectors like LISA, Laser Interferometer Space Antenna, will search for primordial gravitational waves. These could come from bubble collisions in eternal inflation. If detected, they'd provide direct evidence of collisions and multiverse structure. Galaxy surveys. Large-scale structure surveys like DESI, Dark Energy Spectroscopic Instrument, map the distribution of galaxies. These surveys can measure density fluctuations at very large scales. At extremely large scales, eternal inflation might predict subtle deviations from scale invariance. Measuring these could constrain eternal inflation. Fast radio bursts. Some exotic eternal inflation models predict signatures in the distribution of fast radio bursts or other transient phenomena. As surveys of the transient universe improve, constraints on these models will improve. Quantum gravity tests. Experiments testing quantum gravity predictions, if they can be made, would constrain theories like string theory that underlie eternal inflation. Tests of Lorentz invariance, searches for extra dimensions, and studies of black hole evaporation could all provide hints about quantum gravity. Computational approaches. Advances in numerical simulations could allow physicists to compute predictions of eternal inflation more accurately. Machine learning might help identify patterns in large CMB datasets that indicate bubble collisions. Theoretical physics continues to develop new models and refinements of eternal inflation. Slow roll violations. Some recent models explore eternal inflation with violations of the slow roll approximation. This allows for more exotic inflaton dynamics and potentially different observational signatures. Multi-field inflation models with many inflaton fields, rather than one, can produce different eternal inflation scenarios. Multi-field models can create a richer structure of bubble universes. Holographic cosmology. The holographic principle from string theory suggests the universe can be described by a lower dimensional theory. Some researchers are exploring how eternal inflation emerges from holographic descriptions. This might provide new insights into the multiverse structure. Modified gravity. Rather than scalar field inflation, some models use modified gravity theories to drive cosmic expansion. These models can produce inflation and eternal inflation through different mechanisms. They make different predictions and might be testable. Bouncing cosmologies. Some models propose that the Big Bang was preceded by a contracting phase, a bounce. Eternal inflation in bouncing cosmologies has different properties than in standard inflation. These models avoid the initial singularity. Cyclic universes. Ekpyrotic and cyclic universe models propose that the universe goes through infinite cycles of expansion and contraction. Eternal inflation might occur within each cycle or across cycles. This offers another perspective on the multiverse. These theoretical developments keep the field vibrant and evolving. What is the current consensus among physicists about eternal inflation? There is broad consensus that inflation itself occurred. The CMB observations provide strong evidence for inflation. Most cosmologists accept that inflation is an important part of our universe's history, but consensus on eternal inflation is weaker. Many physicists believe eternal inflation is likely correct, but not all. Some reasons for acceptance. Eternal inflation emerges naturally from many inflation models. The predictions match observations. It provides a framework for understanding fine-tuning through the anthropic principle. Leading theorists like Lind and Guth support it. Some reasons for skepticism. It predicts unobservable universes beyond the cosmic horizon. The measure problem remains unsolved. It might not be falsifiable, depending on philosophy of science. It requires string theory or other speculative physics. Some physicists find it philosophically unsatisfying. Notable skeptics, Roger Penrose is perhaps the most prominent skeptic. He argues eternal inflation is not scientifically testable and proposes an alternative called conformal cyclic cosmology. Paul Steinhardt has criticized eternal inflation and the string landscape, arguing for alternative approaches. Sabine Hossenfelder has written critically about the testability of multiverse theories. Notable supporters Alan Guth, who invented inflation, supports eternal inflation. Andre Linde, who proposed eternal inflation, remains a strong advocate. Max Tegmark has developed sophisticated frameworks for understanding the multiverse. Current state. The field is in active debate. Eternal inflation is mainstream but not universally accepted. Observational data might resolve the debate if future experiments provide signatures of bubble collisions or other multiverse phenomena. Alternatively, theoretical advances in quantum gravity might show eternal inflation is inevitable or impossible. The next 10 to 20 years should see significant progress in understanding whether eternal inflation is correct. Let me trace the logical chain from first principles to eternal inflation's conclusions. Step 1. The inflaton field. We start with quantum field theory in curved spacetime. The inflaton is a scalar field with a potential energy V of phi I. The field's energy density drives cosmic expansion according to Einstein's equations. Step 2. Slow roll inflation. For certain potential shapes, the field rolls slowly down the potential. During slow roll, the potential energy dominates the kinetic energy. This creates approximately exponential expansion. The expansion is so rapid that quantum fluctuations are stretched to cosmic scales. These fluctuations see density variations that grow into galaxies. Step 3. Quantum fluctuations and randomness. During inflation, quantum fluctuations jiggle the inflaton field. In some regions, these fluctuations push the field up the potential. In other regions, the field rolls down toward the minimum. This creates spatial variations in the field. Step 4. Eternal inflation. Because the volume expands exponentially, the regions where the field is pushed up represent an exponentially growing volume. This volume contains enough energy to sustain more inflation. This inflating region produces more quantum fluctuations, which create more regions where inflation continues. The result, inflation never completely stops. It continues eternally in expanding regions while stopping locally in bubbles. Step 5. Bubble nucleation. In some regions, quantum tunneling allows the field to transition to a lower energy state. This nucleation of bubbles is rare, but has a probability determined by quantum mechanics. Over the infinite time and volume of eternal inflation, bubbles inevitably form. Step 6. The multiverse. Each bubble becomes its own universe. Inside, the inflaton field oscillates and reheats, creating a hot plasma. This plasma cools and evolves according to the laws of physics in that bubble. Infinitely many bubbles form with potentially different physical laws. Step 7. Observation and selection. We find ourselves in one bubble, our universe. We observe the physical laws of our bubble. These laws happen to be compatible with observers. If they weren't, we wouldn't be here to observe them. This is anthropic selection. The logic is self-consistent. Each step follows from the previous one. The only assumptions are, General relativity and quantum field theory are correct. The inflatoned field and its potential exist. Quantum mechanics applies to space-time and fields. These are reasonable assumptions based on current physics. Given these assumptions, eternal inflation follows as a logical consequence. The conclusion is not that eternal inflation must be true. Rather, it's that eternal inflation is a natural prediction of our current best theories. Eternal inflation and the multiverse represent a paradigm shift in cosmology. What are the major insights? Insight 1. The universe is infinite. Before eternal inflation, we thought the universe might be finite. It had a definite beginning and would have a definite end. Eternal inflation reveals the universe is infinite in space and time. Infinitely many universes exist. This is a profound shift from finitude to infinity. Insight 2. Our observations are anthropically selected. We once thought the laws of physics were unique and universal. Why these particular laws? Eternal inflation suggests there are infinitely many possible laws. We observe our particular laws because we're restricted to observing a universe compatible with our existence. This is not a full explanation, but it reshapes how we think about fundamental physics. Insight 3. Quantum mechanics creates the multiverse. Quantum fluctuations, which we once thought were microscopic phenomena, shape the universe at the largest scales. Quantum effects during inflation create variations that lead to eternal inflation and bubbles. Quantum mechanics is not just a theory of atoms. It's the foundation of cosmic structure. Insight 4. Time is not universal. In eternal inflation, different observers experience different times. An observer outside a bubble sees time pass slowly due to gravitational time dilation. An observer inside the bubble experiences normal time. Time depends on where you are. This challenges our intuition that time is a universal parameter. Insight 5. Fine-tuning becomes inevitable. The apparent fine-tuning of physical constants, the fact that they seem perfectly designed for life, becomes inevitable in the multiverse. If universes with all possible constants exist, observers must find themselves in universes with life-supporting constants. We're not special. We're just in one of the rare habitable bubbles. Insight 6. The Big Bang is not unique. We once thought there was one Big Bang that created the universe. Eternal inflation reveals that Big Bangs are common. Every bubble has a Big Bang marking the beginning of that bubble's observable universe. The original Big Bang is just the earliest of infinitely many. These insights reshape our understanding of the cosmos, time, causation, and existence itself. Despite the progress, many mysteries remain. Mystery 1. The origin of inflation itself. Eternal inflation explains how inflation continues and creates bubbles. But what triggered inflation initially? Why did the universe begin in an inflating state? What are the boundary conditions at the Big Bang? These questions remain unanswered. Mystery 2. The nature of time. In eternal inflation, time is defined locally within bubbles, not globally. What is time fundamentally? Does it emerge from quantum entanglement? Is it an illusion? How do we reconcile quantum mechanics atemporal formalism with our experience of time? Mystery 3. Quantum gravity at the Planck scale. Eternal inflation assumes space-time is smooth and classical, except for quantum fields. But at the Planck scale, space-time itself becomes quantum. A complete theory requires quantum gravity. We don't have a definitive quantum gravity theory. The behavior of eternal inflation near the Planck scale is unknown. Mystery 4. The measure problem. How do we assign probabilities to different bubble types in an infinite multiverse? The measure problem remains unsolved. Without solving it, we can't make definite predictions about the probability distribution of physical constants. Mystery 5. Why these laws of physics? Eternal inflation explains why we observe life-supporting laws, but it doesn't explain why the string landscape has 10 to the power of 500 vacua. Why does the inflaton field exist? Why do these particular quantum field theories arise? Why these symmetries? We've just pushed the why question back a level. Mystery 6. The nature of consciousness and observers. Eternal inflation raises questions about consciousness. If infinitely many conscious beings exist across the multiverse, what is the significance of our consciousness? Are all our possible experiences, good, bad, boring, exciting, necessarily realized somewhere in the multiverse? What does it mean to be an observer in an infinite universe? Mystery 7. The ultimate question. Why is there something rather than nothing? Eternal inflation provides a mechanism for creating universes from quantum fluctuations, but it doesn't answer why quantum mechanics exists. Why are there any laws at all? This may be the ultimate question, and science may not be able to answer it. As we conclude, let's step back and consider what eternal inflation means for our understanding of science, philosophy, and human meaning. What is science? Eternal inflation challenges us to reconsider what science is. Science has traditionally meant making testable predictions about observable phenomena, but eternal inflation predicts unobservable universes. Are we stretching the definition of science? Or is science broader than we thought? Perhaps science includes logical deductions from our best theories, even if the deductions lead to unobservable conclusions. We accept theoretical predictions about black hole interiors and the far future, which are unobservable. The multiverse might be in the same category. The role of mathematics. Eternal inflation is deeply mathematical. It relies on precise equations, symmetries, and logical deduction. This raises a philosophical question. Why is mathematics so unreasonably effective at describing the universe? Is mathematics discovered or invented? Does the multiverse actually exist? Or is it just a mathematical construction we've created? These are ancient questions in the philosophy of mathematics. Eternal inflation makes them urgent. Human meaning in an infinite universe. For many people, eternal inflation diminishes human significance. If we're one person in one civilization, in one universe among infinitely many, how can our lives matter? But perhaps this perspective is too narrow. Even if the universe is infinite, our local experience remains meaningful. The relationships we build, the knowledge we gain, the beauty we create, these matter to us and those around us. The cosmic insignificance of eternal inflation doesn't negate local meaning. Moreover, the fact that we can understand eternal inflation, that we can comprehend the structure of the multiverse, is itself remarkable. We are part of the universe that has become conscious of itself. This capacity for understanding is profound, even if our physical scale is small. The wonder of science. Ultimately, eternal inflation is an expression of the wonder of science. Science reveals a universe far more vast and complex than our ancestors imagined. The cosmos is not a static backdrop, but a dynamic, self-generating system. Quantum mechanics transforms matter and energy into infinitely many possibilities. From simple laws emerges incomprehensible complexity. This is deeply wondrous. The limits of knowledge. Eternal inflation also reveals the limits of human knowledge. We can theorize about an infinite multiverse, but we can never directly observe it. We can calculate probabilities in an infinite ensemble, but we can never verify them with certainty. We can search for the ultimate explanation of existence, but the deepest questions may be unanswerable. Science progresses by asking better and better questions. But some questions may not have answers, not because we lack the technology, but because the questions transcend what any finite being can know. The journey continues. Eternal inflation is not the end of cosmology. It's a milestone on an ongoing journey of understanding. Future observations will test the theory. New theoretical frameworks will emerge. Quantum gravity will eventually be understood. The story of the universe will continue to evolve. What we've learned is that the universe is stranger, more vast, and more wonderful than we ever imagined. And the search for understanding continues. We began this exploration with a simple question: what is eternal inflation? We've journeyed through quantum mechanics, general relativity, cosmology, and philosophy. We've seen how quantum fluctuations during inflation can prevent inflation from stopping. We've explored how bubbles nucleate, creating universes with different physical laws. We've confronted the philosophical implications: infinity, determinism, anthropic selection, and the meaning of existence. We've acknowledged the puzzles that remain unsolved: the measure problem, the origin of the inflaton, the nature of quantum gravity. And we've considered what all this means for science, philosophy, and human meaning. The story of eternal inflation is still being written. Future discoveries will fill in gaps and answer open questions. But even now, we can appreciate the elegance and audacity of the theory. From quantum mechanics and a simple potential energy curve emerges a cosmos of infinite complexity. This is the power of science, to reveal hidden truths about reality. Whether eternal inflation proves correct or is eventually superseded by better theories, it represents humanity's capacity to comprehend the universe. We are stardust that has learned to think about the stars. And now we think not just about the stars, but about the infinite universes beyond our reach. That is the wonder of